of all life on Earth once this balloon gets up there. I'm going to probably kind of go more on mute because I'm imagining this wind noise is a little annoying for you guys.
Actually, you're just fine.
Am I good?
Yeah.
All right, nice. So I'm just going to do a little pan here so you can kind of see the view here and around this way. That's the Albany Hill. And, I'm sorry, what's that?
Cool. You are on YouTube, I think.
Yep.
Oh, great.
Got to make sure that everyone's muted who's watching on YouTube, including me.
Great. All right. So I am actually going to, everything's getting tangled up now with the wind. Oh, that's fun. All right, hold on. Let's go. All right. Most important thing when you launch something is make sure things aren't tangled up, right? All right, so Liam, I will let you lead the parade here, and I'll just kind of show what we've got going on here.
Yeah. Okay. So I'll talk a little bit about what it is that is going on there with Ted's setup. So you'll see that he's got this, rather small metal mylar balloon there, which sort of almost looks like it has just a little bit of helium in it. They're really not all that big, but below it, it's got this tiny little thing that is showing this little device. It almost looks like its own little satellite, but what this is a dedicated computer board, sort of an Arduino, if you've heard one of those, of a microcontroller, and it's got a number of sensors on it. But the key aspects of it that's going to make things really work for us today are that it has a GPS tracker. It has a radio transmitter that actually transmits on the ham radio bands, and it has some mini solar panels. I mean, this is just so extraordinary. It's created by a NASA engineer by the name of Bill Brown, who works in Huntsville, Alabama at the NASA center, the Marshall Space Flight Center there, on much bigger things than this. He actually works on SLS, the new NASA space launch system. But this little device here has everything needed to allow us to track it as it goes up into the atmosphere. It usually reaches up to around 30,000 feet or so. And these have been known with some particularly specialized balloon setups. This has been known to circumnavigate the Earth 7 times just on this little thing here. So what goes on is the solar panels are what obviously provide power to this whole unit. Now, you may notice that where Ted is right now, it's pretty cloudy. And the one thing you need in order for this to actually work best is no clouds. This being a tiny little device here, it really is reliant upon very bright sunlight in order to power everything. So I think those of you that have come through the YouTube link and things, you would have seen the posts actually have a link to the web page that will allow you to track this once it's up. But we're pretty much going to have to wait until it's above that cloud layer. And
it's interesting, Liam, those clouds that Tony's seeing, if you look at, or Ted's seeing, if you look at my second screen there, according to the weather map, there's not much there. So those must be really low level clouds.
They are. It's our typical fog in the morning type of thing. Not bad. Deck is probably under a mile, 4,000 to 6,000 feet, I guess.
Yeah.
All right, so it's kind of blowing here. I'm just going to go ahead and let her aloft.
Oh, yeah.
Is there anything else you want to share about the Pico Hab, about the Sky Tracker?
Anything you think I may have missed there?
Oh, you know what? Let's do this. Tony, I think there's a video I did last night.
Oh, yes.
I refilled this balloon.
Right.
I know the steps and getting this thing set up, and I'll let it go.
Okay, hold on a second. Let me share my screen.
And I'm sorry, guys, I did it in the vertical position like this. But
We'll forgive you this time.
Yeah. At the bottom, you'll also notice there is a URL if you want to track this balloon. And as Liam said, that's going to have to get above the clouds before we get some power to those panels. You'll notice it has a hashtag at the end.
Party balloon. So you put a little intake here, just a straw. It's going to be filled up with helium. And what we're going to normally be doing for our larger text balloon hose with a connector. And a regulator in here. 125 helium. We need that much in here. We're only going to big feet to get this thing aloft. And so that's the balloon. All right, so we're just about ready to launch this balloon. The first thing we want to do after we filled it up with helium is get just the right amount in there where the balloon is neutrally buoyant. It floats in the space that it's in. You can see that it's a little on the heavy side. I'm going to call it good. It's about 3 grams positive lift. When I said neutrally buoyant, that was with an added weight, included the calculated weight of the sky tracker here, at the end of the line. And what I've done is added nickel, which is equivalent to 5 grams of mass. And you should see the balloon fall slowly. All right, then what we've done is we've swapped out the nickel for a penny, about 2.5 grams, equivalent of weight. So we're going to see that the balloon is going to drop slowly. And so using a nickel and a penny, we're able to get a calculation that we know we're going to be lifting between 2.5 grams and less than 5 grams of lift. We're going to be able to send.
So that's our predicted path right there, thanks to NOAA. And we can share that to everyone as well. It looks like it starts off with a potential for a little bit of rain. So 1 inch of rain here. It takes a little bit of time before it gets out of California. And it's going to scoot across the country if we're all lucky and be on the eastern seaboard out toward Michael there in New York in a couple days. And then the model basically says it looks like this one's heading to Europe. So what's going to happen is I'm going to let this thing go with the help from you guys on a countdown. And we're going to go back to our regular show. We'll just check in when it pops up. We can start tracking it. Now, every Friday until June 1st, which is actually not a Friday, I think it's a Tuesday, where we're going to be launching one of these where you can track them as they go around the world. Liam said if we're lucky, maybe we need a little better balloon, but we could potentially circumnavigate on these later episodes. You guys ready to help me with the countdown?
Yeah, sure. Tony, stop sharing a screen so we can see and you might want to spotlight Ted's videos so that it keeps on, because I think we all want to see that balloon launch.
Collectively. All right, we've got the wind's going to be okay. I see the tops of trees there, but I think I'm just far enough.
Wow.
Wow, that's windy.
Yeah.
It is windy, and I'm looking at the clouds here. You can see the dark and the light there, probably.
Oh yeah, and the rain
yeah,
band
we're right
over
in
there.
front of it. So let's let it go, okay? And
Yeah.
we'll back to our regular show. All right. So how about a 10,
9, 8,
7, 6, 5, 4, 3, 2, 1.
It's going to drag across the ground.
Lift off.
It's going sideways.
Drag it across the ground.
All right.
It's going to get caught right there. Go ahead, let it go. Thank you. That's perfect. No, that's what we want. It's got a tracker on it, and it's going to go to New York and probably over to Europe. There you go. All right. And thanks to our neighbors off the fence and out to the air. And so I'll just keep an eye on it here. And it's lifting up pretty nice. It was pretty high winds right there. It was just scooting across the ground.
Very cool.
It was less than, I think it's only about 6 feet tall. And there she goes. So that's heading in a northeasterly direction. Yeah, probably more north, I guess. But it's ascending pretty nicely. And we use that good helium in one of those big old tanks. Not that stuff you pick up at the mart for your special party. So that's kind of nice. A nice good lift. We're expecting 8,000 to 8,500 meters altitude, about 27,000 feet, I guess. And we'll just have to wait for those panels to charge up. So why don't we hit our regular show? To our friends from South Africa on?
We almost there. Thanks.
All right. Hey, that's what. Great. Well, it's good to see you guys.
Yeah, well done, Tony. Ted.
Tony. See, people confuse us all the time. He's the good-looking one. It's really easy to remember. I'm the guy that always forgets to shave.
Yeah. And great demonstration of social distancing balloon launch.
Oh yeah, right. Well, assistance too. Yeah, should I put my mask back on? They're gonna bust me. Better. All right. So now, do we have some of our students with you, Fatima, this morning or this evening?
Most definitely, we've got about 15 students here, 14 students here with you today. Very
fantastic.
excited.
Oh, that's awesome. And so why don't we talk a little bit about, you're planning to do one of these balloon launches also, isn't that correct?
Trisha, yes, is looking into that, and Shivar. So
yes, we're currently looking into it.
Oh, there you go. Hey, Shivar.
Hi, good to see you.
Yeah, good to see you. Now, each country's got their own kind of rules, and we're a little more lax here in the United States from putting something up in the air. I understand the UK, for example, is very restrictive in what they can do.
Yeah, we have the same problem in South Africa. So there's actually no law or anything that covers it. But if it doesn't have a transponder, then we won't be able to launch it.
Yeah. Our stuff.
So did you say if it doesn't have a transponder?
Exactly. Yeah.
All right. So does it sort of, because ours, this one does have a kind of a transponder because it does transmit its position, but it may not be the kind of transponder that they might be looking for.
Like an aircraft black box type thing.
Yeah.
No, so does it have is it the GPS tracker?
It does have, it has its own GPS on it. But it transmits its position via a ham radio band. So there are generally two styles of high altitude balloon sort of things. And the one that allows you to have a much heavier payload, they often, in fact, Magnitude does this a lot as well. They include on it a fully, self-contained battery run GPS tracker that uses satellites. So it actually transmits its position anywhere across the Earth via a communication with a satellite. So that may be the kind, I'm just making up, that may be the kind of thing that they're looking for. But in this case, it's required that the solar panels on the device are activated by sunlight in order for it to track, and you have to have a radio station on the ground picking it up. So that's probably something that we can check on later on, as far as whether the PicoHab does it or whether you'll need, a slightly different setup for your high altitude balloon launch system. But we'll check into that.
The other issue that we've come across is, because I've looked into it, is the altitude. So the 27,000 feet, right?
Yeah, that's this one. Yeah. 27 to 30,000 feet. This one goes.
How high did it go?
They can get a little bit higher if you use a slightly different balloon, and also with this probably doesn't work very well for a school type situation, but if you use hydrogen, I believe it actually goes higher up. So the other type of high altitude balloons where you have a latex balloon type of setup and you fill it up with more helium, those can reach 100,000 feet and then they burst up in the stratosphere. So
that's a good point, Liam. Is Samantha McCoy, has she joined us this morning?
Yep, she's on.
Oh, hey, Sam. So you've actually got a lot of experience with the latex balloons. You want to just say hello and maybe share a story about some of the stuff we've done with you out there in Lodi?
Good morning.
Hey, Sam.
I'll talk about my experience. So, can you guys hear me?
Yes.
Okay. So I've done it a few times, and my kids have always loved it and enjoyed it. Our very last one, we lost the balloon for, I want to say, for about 2 years. And then out of the blue, a stranger, because we had a note on it, and a stranger just emailed me and said, I found your balloon. So that was really exciting. Very exciting.
Yeah, it was a nice little gift. Now, we knew exactly where it was, but it was off the Pacific Trail there in the Sierras at around 10,000 feet elevation, and it was on a cliff edge. And apparently, we would need at least a 2-day hike to get up there, and you'd have to spend a day to acclimate and what have you. And honestly, we just said, well, we hope someone would get it. Eventually, we'd have to go up and get it. And sure enough, some person from Southern California was out on their weekend hike, and they were just scrabbling through the rock and going down the more difficult path. And they said that they found something that was shiny, and sure enough, that was bits of our balloon and the payload. And so, how about that? That was our longest recovery ever.
Yes.
And well, what's nice about those also, Sam, is your students get a chance to do some engineering design work in the payload, right?
We did, yes.
So thinking about at this altitude, when you're in the stratosphere, at about 100,000 feet, the air pressure is about 1% of the pressure that we have here on the surface of the Earth, which is pretty amazing. And it's also really, really cold. If we look at the temperature, minus 40 C or minus 50 C, and we look at the pressure, it's about equivalent to being on Mars if you were on the surface of Mars. So if you ever want to do some investigations and think what might it be like on Mars, that's a good place to go. Of course,
Looks like we might have lost Ted for a second there, which can happen. So we'll just have to entertain ourselves now without the benefit of Ted. You may just, but anyway. So anyone else checking the tracking link right now? So I'm gonna, for those of us on the Zoom side of it, I've just posted the tracking link if you want to follow along, but it's certainly not appearing there at the moment.
That's number 2, right, Liam?
Say that again. Yes.
That's number 2.
Yeah. Kilo 6, uniform Quebec -2. And just so as you know, so each sky tracker, each of these little things here, is programmed with the ham radio call sign of the person who is in charge of the launch, because the rules of this is that it must be under the control of a registered ham radio person. This is how it works in the States. And KK6UUQ happens to be Ted's ham radio call sign. And the -2 is just a notional number that has been assigned to this particular unit here, and that allows us to do the tracking. While we're waiting for Ted to hopefully come back online, so I've only done one of these high altitude balloon launches. I've done another one of the PCAP things, and they are just so awesome. I come to this, you probably see with my shirt here, for anyone who doesn't know me, I do stuff with the International Space Station, track it. And there's aspects of this that very much are sort of similar to the types of things that can go on with a satellite in terms of the communications. a satellite has to have a method of getting its information, its telemetry, which is just another name for the data that's being collected on this, down to the ground. So in a way, it does provide sort of a compatible experience for students around what it is to work with satellites. And particularly the other type of high altitude balloon launch where there's more of a payload and students can put other experiments into it. There's often additional opportunities there to get a lot more data captured as well. So it's all very exciting anyway, but I just love the fact that this looks like a satellite and it acts like a satellite in a way, although it's going a little bit slower, obviously. A little. Oh, there you go. You're back at home.
I am.
Awesome.
Yep. I had to wash my hands and get a cup of coffee.
Yeah, that's right. Cool. Wash your hands.
Yeah, that's right.
Very cool.
Hopefully that wasn't too noisy or windy. So that is thanks to, we had that experience thanks to Lodi Unified School District. As I was mentioning at the top of the hour, they've been working with us for about 5 years here at Magnitude. And they were the first school district to actually run the ExoLab. And Sam has been with us from the very beginning. Sam was talking a little bit earlier, and she's at Krista McCullough, if you know that astronaut name, Krista McCullough Middle School there. They also have Ronald E. McNair High School as well. So they're quite fans of the space programs out in the Central Valley of Northern California. And a lot of people think that all the action is in Silicon Valley and, that everything's happening in San Francisco, but really we've realized that the action is out there in San Joaquin County in the agricultural region. It's become a bedroom community. Everyone's moving out there because you can get a house twice the size for half the price. Well, it used to be anyway. I think it's changing. And the schools and the districts are really, Lodi has about 32,000 students, I think, if you look at all the charter schools and everything else. So it's a good sized district. Their libraries actually connect, all of their libraries in their primary and middle schools are connected to the International Space Station through the ExoLab. And I don't know if we have any photos we can share, but the librarians curate fiction and nonfiction works that's age appropriate for the students. Without the ability to read, it's kind of hard to do any kind of science investigation. So we're focused with the younger students on numeracy and literacy skills. And we like to do that through the lens of what we do on the space station. And of course, in order to really make those library setups fascinating, we've got the ExoLab with its magenta glow. It's like a bug light. The kids rush over to see what's happened since the last time they're in the library. They visit the library once a week. But they also are able to see a live view of Earth if it happens to be in sunlight, thanks to the ISS above, something that Liam here has invented, and it's really all over the world today. So when they come in the library, they can see Earth right now, and they can see their plant experiment going, and they make that connection. And of course, then the librarians have those books that the kids can check out if they're so interested, whether it's a biology book or book about space exploration or some other kind of story. So we're pretty excited about Lodi joining us. Now, the pandemic has shut down our program to launch these at their schools, kind of disappointed about that. But what's neat is Lodi is now able to share their launches with the whole world at the same time. So we're going to be launching one of these every week. This was the first one in a series. It was number 2 because we launched the first one just before this broke. They have a science festival every year at one of their high schools. Tokay High has the NorCal Science Festival, and all the activities with robots and cool contraptions that the kids have invented, and the work that we do is all kind of showcased there, led by students. So we launched one of these Pico Habs, one of these sky trackers there at that event. And so this is number 2, and we're going to have 7 more. So every Friday we'll kick off one of these. You can get to track it. It should be good entertainment for the next week if everything works. So we'll see what happens.
Yeah, I just learned that some of the Lodi students are not able to watch it on YouTube because they are blocked.
Oh, wow.
Yeah,
okay.
Yeah, I just emailed the IT department.
Okay, well, we'll work through that. Again, this was a kind of a first run. Sam is going to be leading her students through what of our typical investigations will be. And we take about a week before we actually launch the balloon. And this is generally ideal for K through 5, K through 6, 7 or so. We really like to try to get into the engineering practice when they get a little older. So we go to the latex balloons. They go much higher, faster, but we're able to carry a couple kilograms of experiments. And you can do stuff, you want to see if your bag of chips is going to pop, or if your marshmallow is going to get big, or will these seeds grow differently because they've been up there versus the ones you kept on the ground. And so kids do these experiments. If you've ever seen the little tardigrades, these little tiny creatures, they're absolutely fascinating. They're not technically extremophiles, but you can actually desiccate them, take out all the moisture from their body, and they kind of shrivel up into these non-crystallized structures. Their DNA really becomes this odd configuration, but you can expose them to radiation, to the vacuum of space, to temperatures, extreme temperatures for a limited period of time. You can bring them back and rehydrate them, and they're like nothing happened. It's like, wow. So the tardigrades are pretty incredible. And sometimes those are our little, our strattonauts, about leguminauts. So these are little creatures sometimes we put in there. Don't like to fly mammals or anything else like that. If you know it's going to get to minus 50 degrees, you have to ask yourself, is it going to live? And so that usually gets checked off the list pretty quickly when the kids start thinking about what they might want to do. But really, let's go back, because I know it's not the earliest time of the day for you guys. And thank you for your students joining us. Let's talk more and kind of move over to Exolab. Why don't you share with us what you guys have been up to? And as students, I don't know where you are on starting experiment, if you're in experiment 7 now, or if you're helping us determine what our next legume will be for Exolab 8, but we'd love to hear from you guys too. So I'll be quiet and love to hear from our friends there in South Africa.
Okay, so we are busy with the experiment. I've got it right here in front of me. So let me just show you. There we go. So it is now at 5:33 at the moment. But 2 days ago, we started growing some mold. Some started growing in the experiment. So we are going to trying to figure out why that mold is there, and the control is not growing at the moment. Then, so we're going to investigate what kind of mold is actually growing there. We've got some foldscopes. I hope that we'll be able to see what it is and identify it. These are actually growing very nice. I don't know if you are able to see this.
Oh, yes.
Yes, looking great.
This one is the inoculated one, the rhizobium, and is the Martian soil.
Oh, nice.
Yeah, so it's still going in the test tube. I was hoping that there's no mold at the bottom here, but there you can see this one's got nice, beautiful leaves. It's growing at a slower rate, obviously, but looking so beautiful. And yeah, so the experiment is going well. There's lots of things that we can investigate. I think our students have a couple of questions. I don't know if anyone wants to start off with their questions and their curiosity, because it's been a great learning curve for us. It's the first time that most of them, I think all of them, it's their first time with this Exolab experiment. And we are thoroughly enjoying it, because we've got a WhatsApp discussion every day. Every day we have a discussion and questions and feedback and ideas. So I don't know who wants to start off with a question. Anyone there?
Come say hello to the world, guys. Excited to hear your voice, see your face if you've got video.
It seems to be just straight out of the blocks there.
While we're waiting for someone to chime in, I just want to let you know, so the space station's passing over Berkeley in just a few minutes, Ted.
No way, really?
And this is live video from the space station. But the special thing is, it's going to be above South African skies in another 20 minutes after that.
Awesome.
So just so as you know.
All right, big shout out to Expedition 62.
63 now. It is
63.
official.
That's right. Yeah, there you go. All right.
But anyway, so the Exolab experiment that you're working on was up on the space station, came down just a few weeks ago. But just to give you that context.
That's
How did you make that happen?
Yeah, that's right. I just made a call.
Few calls. They just kind of turned it a
hey,
little bit.
guys, can you just do a little reboost, a retrograde,
there you go.
prograde, whatever. Anyway, back to the regular programming. Sorry for the interruption.
All right, students, we'd love to hear from you.
I would just like to know why the cowpea was chosen.
Oh, that's a great question. Where's Mr. Wilkinson? He's jumped off. He's teaching some classes right now. So that is a wonderful question. I think Mr. Wilkinson, Michael Wilkinson, is our lead teacher out of New York. With the pandemic, he's now got the remote classes. He teaches 4th and 5th grade students there in Brooklyn. And I think he has a 4th grade science right now. So he's going to pop back in probably about 15 or 20 minutes. But my understanding was he was very fascinated with this symbiosis between the legumes and the bacteria rhizobia. And it could be that he just kind of liked black-eyed peas, I think. It wasn't really much scientific at all about it. And we're going to take that to heart when we're thinking about our seeds we want to send up on Exolab 8 in February of 2021, just here in about 290 something days. And so we want you guys, anyone around the world, to help us select that next candidate. It will have to be a legume, alfalfa, zucchini bean, mung bean, pea. There are a lot of them. There might even be something on there that you really like, haven't included. But some of those indications of what makes a good candidate may be something that you love the taste. You got a recipe you want to share, or you love the way the plant looks or the flowers that it has. We're hoping for the older students there. It sounds like you're on the older side, that you're going to do some science research as well and support your argument besides it's a beautiful flower. But if we can find a beautiful flower with some great recipes and it's an awesome science prospect, then we're probably going to pick something like that. But that's a great question. What other questions do you guys have?
Can I also just ask, how many plants have been used for the experiment so far, and which showed the best results?
Oh, that's a great question. So our first 3 missions were with a model organism called the Arabidopsis thaliana. It's a part of the mustard family. And Gil there in Japan, since Gil's here, actually does research with that. And so I'm not going to turn it over to you, Gil. Why don't you share a little bit about Arabidopsis before we talk about some of the other microgreens that we've flown?
Hey, guys.
Hey, good morning. Or good evening. Good evening.
Good evening. Yeah, it's our good morning. It's 12:40 here in Osaka.
Huh?
Yeah, so Arabidopsis, you can't eat it. I mean, you can, but you shouldn't. But it is a model organism for genetic studies for plants. Its genome is very small. It's pretty much figured out. But the reason why that plant is used so often is, one, because it's easy to detect changes in its excuse me, my daughter just woke up, in its genetic profile. So if you're looking for specific genes that are being turned on or off due to stressors, this is a really good plant, a good a good organism to observe, because you know what you're looking at when you start, and because the sequence is so short, those changes can be made pretty obvious because of the sequencing. It's been used pretty much, I mean, not just for space studies, but in as a model organism for botany studies all across the fields. And because of that, it's got a very robust database available right now. Not just, like I said, not just in space studies, but for studies within plant biology that have to do with biotech, agriculture, genetics, medicine, bunch of stuff. So even though astronauts will not be eating Arabidopsis, hopefully, it will serve, the data that we collect from the experiments based on this model organism will serve to determine the future of experimentation in space, in agriculture, and hopefully here on Earth as well.
Mm-hmm. Yeah, Jenna. So the idea there, because we see gene expression changes under stressful conditions like microgravity or these higher gravities you might experience in a rocket launch. That's a great plant to study. In fact, Dr. Barker will be joining us a little later. I don't know if he's on right now, but he introduced in our first episode something called SciVerse, which is a data set of genomics around the world, mammals and plants and what have you. And this is a well-studied organism. So those were our first 3 missions. In addition to that, we flew microgreens like amaranth and chard and wasabi. If you like your sushi with that green stuff, wasabi, surprisingly, that's usually not wasabi. But it's what's counts as, they call it wasabi. But growing a true wasabi is pretty hard to do. So we had those as well. And those were really kind of thinking about microgreens if we wanted to have food for a journey to Mars, or we wanted to build a garden on the surface of the moon or something like that. But then and that was flight 4 and 5. But then really, because we're all learning together here, we started thinking about some other benefits or some of the challenges of doing things beyond Earth. And one big thing that I think had us thinking about what Cowpea could do was, where are you going to get the fertilizer from? There is no soil on Mars or on the moon. It's just rocks, right? So dirt. And so where are the organisms? And these bacteria fix nitrogen, and one of the key ingredients for plants to grow outside of, what are the other 2 gilts? Potassium and phosphor, right?
Mm-hmm.
NPK, and that concentration is going to give you what you really need. Here back on Earth, whether we're in sub-Saharan Africa or in the Gobi Desert or in like the Mojave, we have some big challenges of growing something in those places as well. So our thinking here is, if you could grow something on Mars, you can probably grow it here on Earth easier, right?
And Ted, if I could jump in really quick as well, anything that we're going to be adapting to or using abroad and on the moon or the ISS and on Mars, like you said, can be adapted here. However, all the testing required for that's going to need a very robust data set, right? And another reason why Arabidopsis is such a good target organism to use, it's got a very, very short life cycle. You can grow a lot of it. It's got it grows very quickly into maturity. It needs a very relatively small amount of space to grow in, and it has the potentiality for self-pollination. So with such a small organism with a well understood genetic profile that grows so quickly in such a small place, you can start really seeing patterns pretty quickly. Mm-hmm. So these patterns, because of the stressors, whether they're radiation, temperature variance, or gravity, will start kind of writing stories about the things that we should be looking at for these systems to be used on the moon or on Mars, and hopefully here on Earth to make food production here better.
Awesome. Hey, some more questions from our friends in South Africa. And I'm just going to note here, Liam alerted me that we are getting transmission now from our balloon, and just about you can see I launched from down here at the waterfront. Zoom in, and it looks like, it's kind of circling around here. It's heading over the Berkeley Hills. Actually, this is more El Cerrito, but it's like and it's heading over to we're in Contra Costa County now, a different county, heading east. It looks like it's doing a little loop-de-loop climbing, which is good. Anyway, more questions. Jenna, thank you for those questions.
Hello everyone.
Hello.
I want to ask, how is this experiment? Do you plan to take the experiment like with the planes on Mars? Like, how do you plan to go with it on Mars on a 6-month journey, example?
Yes. And so I heard most of that, and then please fill me in if I missed part of it. How do we plan to grow these plants on Mars plus a 6-month journey? Is that it?
Yes, it is.
Oh, great, Christian. Thank you for asking that question. So, well, was it last week or the week we had an exogeologist, actually a former chief scientist for NASA joined us, Dr. Ellen Stofan, and she knows a lot about the different planets here in our solar system and even the exoplanets as we start getting information about what those are in farther systems and galaxies away. But we have a really high salt concentration on Mars. And a little later in our program today, if you can stick around for that, we're actually going to be investigating, and we have a chemistry chat in kitchen chemistry. Think about solutions and how you get like 1 mole of whatever liquid and get it down, break it down into different concentrations and dilutions. And what is kind of the optimal, well, obviously having no salt, and there's some interesting history around that as well. So there's going to be some big challenges on doing something on Mars. As far as what we do from here launching from Earth, whether we're launching directly from Earth or maybe from the gateway, which will be out near the moon and heading to Mars. These questions that you're asking, Christian, right now are questions we still need to solve. So if you're thinking about it, we'd love to hear your thoughts. Should we just send the seeds and grow them when they get to Mars? Should we grow them in space and should we start on the ground first? What will happen when the seeds are in their 3rd, 4th, or 5th generation? Will they change genomically, right? Will they start expressing things in a different way? Will they taste funny, right? Will they be better or worse for us? Or will they be no difference at all? All of these questions we don't know. And even some of the really smart folks that are doing the advanced research are unsure. They've got some ideas. And so you guys, anyone that's watching this, anyone that wants to participate with our Leguminaut challenge, not only we're trying to find what a good plant will be just to send up for ExoLab 8, but we're really thinking about, well, what will happen? And so I would love you to think about that problem and maybe even write out a little bit about maybe write out a program on how you might approach that. You know, do you recommend we take the seeds safely there? Do we need to protect them from radiation since we're outside of the magnetic field of Earth? You know, do we grow the plants? What kind of light should they have? How do we supply nutrients to those plants when they're growing? All fantastic questions. So thank you for asking that. And I think the jury's still out. Maybe you guys can help us figure out what the answer is on that question. So
Thank you.
Oh, you're welcome. Thank you for joining us. Who else do we have? I see a lot of students. Speak on up. We want to hear your voice. And thank you for joining us too.
Doesn't look like anyone wants to ask any questions. They all
right.
We're also excited. I think they're also fascinated about everything that's happening at the moment.
I have one more question.
Oh, great.
So you said that the different missions have different objectives. Can you share how many different missions and what the different objectives were on the ISS?
Oh my goodness. Oh, so we're just a sliver of all the awesome things that are happening up there. And I'm going to ask anyone else to weigh in here. Dan, maybe you want to share some of the experiences that you know that are up there. Dan is coming from Canada. And so, you know, we've got folks from around the world here. We were talking to Gil in Japan. And I know you've got some experiences of different experiments up there. So other than ExoLab, we've run 7. They've all been plant-based. And now we're adding some bacteria for this symbiotic relationship. But there are other cool things that are happening up there. Danny, you want to share a little bit about some of the things that you know are happening up on the space station?
So in terms of the plant growth, we're fairly new to this program as well. So I can totally understand. Fatima, congratulations on the plant growth. It looks amazing. And hey, students, wow, you got your smarts on today. Fantastic. So what we're doing is I've been involved a lot with Tomatosphere. So a lot of my involvement with the International Space Station has been about growing tomato seeds and replanting the seeds when they return back from the space station. And that's been about, good 6 years, if not more, running. Really great results. I have students right now, and I'm hoping that they're on and listening on Facebook right now. And they are planting and have planted the Tomatosphere plants that have been returned from David Saint-Jacques and the previous mission before. So 2 of our Canadian astronauts. Now we're super excited to be part of this program so that we can investigate glycine max soybeans, perhaps being one of the chosen beans to go to the International Space Station. So our involvement has really been mostly through the tomato sphere, but now so with Magnitude, super exciting about that. And anything that you can do to get more involved in this program is really, really worth it. It's a great experience, folks. A really quick question I have for South Africa is, what beans do you have in South Africa that may be really cool candidates to be grown with the EXO lab that would go into space? Because we can actually learn something from you guys.
That's a great little tennis match. Back to you. Yeah. So if we think about a legume in South Africa, what's familiar to you guys?
What should be considered before choosing a seed?
Ah, wow. You've got your science hat on. Well, let's see. We have some considerations, and we're looking at the United Nations has something called Sustainable Development Goals, SDGs. And there are 17 of them. They're really hoping to make a better planet. And we're following 2 of those goals. One is zero hunger. We don't think anyone should be hungry ever. And so we're going to need to make sure we have food that can supply people, whether they're going to be going to Mars or they live in somewhere in the world that they don't have really good nutrition, whether it's here in the United States or anywhere else on the planet. So one of our considerations is this a nutritious plant? Is it energy hungry? Does it really need a lot of water? And that's going to be a tough thing, especially in different parts of the world if we have dry environments. Is it really sensitive? Does it have to have perfect temperature and, like an orchid or something like this, and have to have the perfect soil? Or is it really kind of a resilient plant? Like, put me in anything and I'm going to grow, right? And so we want a robust, resilient plant that's full of nutrition, that doesn't use a lot of energy. And if it has some added benefits, like in the case of the legumes, when it works with the rhizobia, we're going to get an extra nitrogen in our soil that we're creating, and we'll end up with a better quality food in the future. And so I think these are some of the, and any other of our educators want to weigh in on this, these are some of the key things that we're looking for in a candidate in our experiments with ExoLab currently.
Well, it's similar to like azuki beans. They need to be nutrient dense.
I see what you guys are doing. Glycine max there, and
any crop, especially one that's got so many antioxidants and it's anti-anemic, like azuki beans, obviously. They're gonna be very, very important to that to future space missions. They have to be nutrient dense, high yield, nutrient dense, with minimal effort, really. Like the least amount of attention you have to pay to the crop, the better chances you're gonna have to flourish in space. Like azuki, just putting that out there.
and the same thing goes for lentils.
And anyone else watching on YouTube or Facebook, our principal investigators here, some of the teachers, are actually asked to support a particular legume. So Diana, there's a little nod out to Max or soybean. There's her little rocket. And Gil there in Japan is focused on azuki bean. We have a number of legumes. There's alfalfa, there's clover. I think the crimson clover or red clover is what's currently being investigated. White clover isn't currently in this set. Green pea, chickpea. So there are many different ones. And so they all have kind of different characteristics: fast growth, slow growth, different amino acids, different ratios of carbohydrates and proteins. And all of these things we are taking into consideration. So any of our teachers that are running the experiment now, do you want to share?
Is trying to get in.
You completely left off lentils on your list there, Ted.
Multiple times.
I'm personally offended by that. However, lentils are, pretty well packed with nutrients as well. And not only can you eat the seeds? But the sprouts are amazingly dense with nutrients. Now, this particular plant that I'm showing you guys, I have put this in a mixture of coffee grounds and regolith, Martian simulant regolith. Got some right here from the Mars Garden. And I germinated this one about 4 days ago, put a little bit of the rhizobia culture on it, and I've just been giving it a little bit of water every day, and it's growing nicely. And I am just growing this on the kitchen counter in my house. I haven't put it in a window or anything like that. So there's all sorts of, you don't have to have the best scientific equipment around to run these experiments. Use whatever you have. This is a K-cup that had coffee in it. Put a mixture of the coffee grounds with the regolith and a little bit of rhizobia just to see how it's going to grow. And it's looking pretty good so far. So.
Yeah, mine are getting a little leggy, Gil. I mean, Steve. So
yeah, I've got some that are growing in a beaker just in regular potting soil, and they're getting pretty long, getting pretty tall. But so I'm curious as to what the regolith might be doing with this one.
Mm-hmm. Yeah, this one seems to be really reaching to the light faster than everything else. So I'm curious if it just really wants to get that extra, solar radiation or what have you.
Yeah.
Exciting stuff. So all of our teachers have something they want to share with us, definitely. Let's see.
Can I just add something, Ted, quickly for the students? And that's that we are doing on our side in Canada, we're working with tea bags. So we are starting off some of the germination right in tea bags, and we're also planting. And then the nice thing about it is it's all compostable. So if you consider any plants and the ways that you wish to plant them, tea is something that we have all across the world, and maybe you want to explore that as well.
Mm-hmm. That's good advice. And I see that Javier has joined us from Houston, really helping us with our Latin communities. Good morning.
Good morning.
Good to see you, or it's good afternoon. That's still morning.
Hello, guys.
And Lori's joined us as well from Florida. Hi, Lori. So we have our students from South Africa on the line, and we heard a couple questions. So I'm going to be quiet again and see. I know you guys have got some more questions or some ideas. Don't have to be a question. Maybe you've got an idea about what we might want to do after you've heard a little bit about the ExoLab 8 objectives.
I saw you again.
Hi there.
Yes, Jenna.
Oh,
Jenna.
You asked about the different legumes in Africa that we could use, and the only ones I could come up with that are sort of a staple food for us would be split peas, lentils, pinto beans, chickpeas, all of that. Daily.
I think Steve there in Atlanta, just outside of Atlanta, is pretty excited that you said lentils.
Lentil.
And Leonte,
Clover.
Michael's back. Hey, Michael, good to see you.
Hi. I just finished my fourth grade science class, who are going to be our Leguminaut challengers with a little Tai Chi break for their weekend to start. So.
Oh, fantastic. Glad to have you back. Our launch, just to give you an update on that before we get back to our students in South Africa, we're about 7,800 feet right now in altitude. And
wow, it was you were like 2,500 when I was looking with the students.
Oh, there you go. And it's on its way kind of northerly. But Leonte Hardy asked a question. Do you love having your job? And I don't know if that's related to you, but yes, I do. But I think if you ask anyone here, it's pretty exciting.
Oh, did we lose Ted?
Somebody forgot to recharge his batteries.
Is anyone close enough to plug him back in?
Well, no, social distancing, Gil.
There we go.
He's at home.
We need a GoFundMe to pay the internet bill. Maybe That's
no, I think it just, I think everybody here loves their job, because this is like too bloody hard to be doing if we didn't love it, right? So that's, we were in another conversation. I can't remember if it was it in this group or if it was another group, but we were talking about just how much, as in terms of educators, how much energy we spend not on the cognitive education, but the social emotional education, and just making sure our students are healthy and safe. And I don't know, I was just saying to my students that I just left, it's like, it's really weird not having you physically here. And the only way I get to interact with you is through this screen. So I just have opened up, they can schedule me. I gave them a You Can Book Me link so they can schedule me for private or small group meets. And a couple of kids have already done that, just because, and one of them just wants to chat about his new telescope. So that's, you know, then that's the kind of thing that they would have done in school. He would have brought the telescope in and we would have looked at it together and done a tutorial, but we'll do the next best thing.
But then with this opportunity, you are connected with a student in South Africa.
Yeah. That's the other piece of it, is we've made this global connection through programs like this, and that's so exciting. I mean, just we've got
right, they are
all kinds of people all over the place here, and just in this screen. So
right, they are talking to a educator in Japan, in Canada, now in US. Yeah, that's awesome.
What's cool about it, if you're asking if you enjoy your job, I think everyone here gets it, but for the students that are taking part of this, guys, you got to understand that those questions that you're asking, some of them, there's some information and some knowledge that's been kind of established on it, but there's so much that we just don't know. Like we don't know, and that's awesome. And those questions that you guys you're coming up with, the experiments you're running, all this stuff could literally change the course of space exploration. Like that's not an exaggeration. It could literally change the way that we habitate in space, and it could change the way that people get access to their food here. So it's super important. It isn't just a gimmicky little project where, hey, look, I grew a bean. No, you literally could be changing the future of the human race, which is awesome. And you could be diminishing some of the suffering here on Earth. So
yeah, this is the conversation I had with my fifth graders who are going to join us later today, and the questions that they've been brainstorming. You got to tune in for that. It's the last half hour of our day. So 14:30 Eastern. Gil, hopefully you can get a nap and come back, or get supper, or whatever time of day it is for you, because there are some really amazing questions, and they get right to the basic science. And I've said this, people here have heard me say this, but people watching on YouTube, your students are natural scientists, and so much of regular school, they've not been afforded that opportunity to truly investigate life. And now that we have to recreate curriculum, you've got a real opportunity to let them let their minds expand and not worry about a test score, to do some real deep learning that they can apply in novel ways. And as Gil was saying, they could solve some major problems that this planet faces, including this pandemic. You never know where these kids are going. We had a couple of weeks ago, we had one of Lori's young ladies who, if that girl doesn't discover something super important, I will be shocked. She is well on her way. The way in which she's thinking, the structure that Lori's given her, the freedom that she's given her to do that, and the support, that's, you've all got students like that. Most of your students are like that. And when they get bored, they build these incredible forts out of umbrellas. Gil's daughters did that yesterday. It's just a delightful picture. And that's what happens when you get bored. You come up with novel things.
So I'm curious what other things you guys like to do besides planting stuff for space. there in South
Yes,
Africa.
that's an excellent book, Javier.
Yes, I like this book. I began to read it. It's from Professor Meet Resnick. He's from MIT. And this book is about how especially kindergartners learn, the way they learn. And he talks about his experience, and he's a great guy. He was the guy who invented the Lego brick, you know, for the robotics and stuff. His team, and he's also behind the Scratch programming environment. So he's a big influence, and I'm pretty surprised that MIT has a big development and research about how kids learn. So talking about, you know, enjoying our jobs and what Michael said about kids being natural researchers and scientists is because kids, you know, are new to the world, and they are beginning to see a lot of things with fresh eyes. They don't know good or bad yet. They're finding their ways, and they have very clever ideas of how things might work, you know, especially things out of the blue. Sometimes, you know, as teachers, we get that a lot. Let me tell you a little bit about my story, how I ended in this pathway. It was because the curiosity of a student a long time ago, when I first began to teach, I run out of ideas, and I began to the students, hey guys, what would you like to learn? And some of them told me about, hey, I would like to learn about horses, about mermaids, sharks and stuff. But it was just one guy who changed the trajectory of my career, because he told me, hey, Mr. Montiel, I would like to go to Mars. Back then, when I first began to teach 15 years ago, we didn't have quite the technology for our students to go and being immersed in a Mars learning experience. So I tried to figure it out the way this student could go to Mars. So I created a series of lesson plans for that specific student to learn about Mars. And then years later, probably, I don't know, 5, 6 years later, a lady from NASA came back to my school, and I documented with pictures and videos about the learning experience of how can you push a small kid to learn about Mars. And those lesson plans, I presented them long time ago, years later, back in 2011 in 6th Space Exploration Educators Conference. And since then, you know, my career took a 360-degree turn, because now I'm involved with this kind of projects, you know, that have an impact to the kids. And it was because of curiosity of a student that he didn't know if he was able to do it. He just brought that idea, hey, I would like to go to Mars, and you know, I was fresh out of college and didn't have a clue either. So I developed those lesson plans that ended in being in front of you. If it wasn't for that specific student, and if I will ignore him, probably I wouldn't be with you guys today.
No, it's so important, Javier. We have to be learners ourselves and willing to boldly go where no teacher's gone before every single day. And if you really pursue the questions that students are asking, you'll be so much more successful in helping them learn, because that's what they're invested in. And as a good teacher, your job is to know what the standards are, what the skills are, and just feed all that into it. And that organic nature, it's so much more powerful.
I agree.
And I really, those that are listening in, educators, maybe you've never tried that, but if you can give yourself the space to do that, it just becomes it becomes play for you as well. I had a similar story my first year teaching, Javier. We were doing surface area of polyhedra. And so we'd done, you know, cubes and rectangular prisms and cylinders. And one of the kids said, well, what about a cone? And what they had done is they'd actually derived the formula. And so I said, I don't know, what about? It probably took us a week to sort it out. And there were periods where the entire 40 minutes, we all just sat there and stared at the board at the work we had done the day before, trying to find some insight. And then eventually kids saw there's a ratio involved here. And then they got it. And they were able to then build the formula, simplify it. You know, and these were 10-year-olds. And so you give kids the space to do real learning. Your kindergartners, think about this, everybody, 5, 6-year-olds, they're learning how to go to space. They're figuring out these big problems already. And if you think, because everything, as Javier said, everything is new to them. What's the difference of thinking about going to Mars than it is going down the street to a store they've never been to? It's the same kind of exciting expedition.
I think I'm 5 years old then.
We should all engage the world like a 5-year-old.
I know, right? Hey, while we still have our friends from South Africa on, I'd love to hear from you also. Maybe something you just want to share with the rest of the world that you like doing down there or you're excited about when you look at the future. What would you like to be as a career? So just kind of a little open forum here for a couple minutes before we get on to our next topic. So
I wonder if they have the fluid shift like astronauts do because they're upside down.
I think we're upside down.
Oh, okay.
I think
yeah, Ted, I'd actually just like to chip in there regarding that, because I think it's so important when you look at the students here in South Africa and what they're actually contributing to, everything, because the shift to, especially down here, the shift to a distance learning platform over the internet, it's quite a challenge. And the fact that so many of these students have adapted so fast to everything, they've collaborated, they've engaged every day when I see them sharing information on WhatsApp and just answering questions every day. It's just, I think it's something that's quite amazing. And I think, yeah, they really deserve something for that.
So Sheba, what we're going to want to do is open up some of our lessons and learning through WhatsApp. So with Tony, let's park that for off this session here, but let's think about how we can engage you in a more meaningful way in the channel that's more appropriate to the way you're communicating together. So let's make that a goal. Okay.
Yes, because anything that provides resources for us that aids in any way, especially now with this whole switch to distance learning, anything is always appreciated.
Maybe that's a question. What do you guys think about distance learning, students, as you're making your adjustments?
Oh,
like,
yes,
how has it been speaking on WhatsApp?
We're actually making a big adjustment, like communicating through WhatsApp. We actually finding new ways, like we can even solve solution. I can even see that it's easy working on WhatsApp and all like online learning than on school, but there's still some challenging also while we are working online here.
What's the most challenging thing for you, Christian?
The most challenging thing that I was used to at school, like you can communicate with your friend, but at home you can't really do that. And also getting space and time, like to go and focus. Let's say you have sibling, they want you to come and play with them or something like that. Parents want to call you. So all that are kind of challenging.
Right.
Yeah.
You have a younger brother or sister then?
Yes.
They want to play soccer or something. You got to get your work done.
Yeah.
I can understand that. And if you students, if you don't want to chat or speak, you can always write a question or a comment in our chat as well. We're more than happy to read that and answer it as well. And feel free to kind of stay on. And I'll just pause for one more second if anyone else wants to chime in there from the beautiful country of South Africa.
I'm sorry, I'm talking a lot.
That's quite all right.
I think it's in a way, it's a lot more difficult online because it's more difficult to communicate, because what if you're busy with chores or something and then you miss out on quite a bit of work because you were busy. But so far the online discussions have been going much better than I expected it would, because you get a lot of input from different people at different times, and you get to really discuss with the peers other than what you could actually do in the limited time you could at school.
There you go. Do you have a chance to turn school off, if you will, or is it kind of always on? Like now that I work in my garage because I can't work in my office, like work is always on, and I have to find a way to kind of turn it off. Is that the same way with you and school, or can you find a way where you can turn it off and go play or have fun?
I think there's really no turning off school or learning, because now that we do it in our own time, we can do it in a space where we're comfortable, and we can sort of take our time instead of sticking to a very constricting 1 hour of learning.
Well, that's interesting.
Students, if you could tell us educators one thing that would make this distance learning experiment that we're all engaged in, that would make it better for you, can you think what that would be?
Questions. Like, if we would have questions, it would be much easier to personally talk to the teacher instead of like announcing it in the group, because a lot of us would be scared to do so, or the question would be overthrown by a lot of other questions from students, and we won't get to have the same one-on-one time you would have in a classroom.
You know, Melissa asks a great question to us, and I'll just pose it to our group here. If legumes can form rhizobial nodules in conditions where gravity is minimal that stimulate good plant growth, how can we revolutionize plant growing here on Earth and potentially on Mars?
That's a great question.
Yeah.
I know an interesting tangent on this. So
I'm not surprised.
This is Dr. Richard Barker for our friends in South Africa. He's out of the Gilroy Lab in Wisconsin, and they really focus on Astro Botany. So he's the right guy to ask that question to. Go ahead, Richard.
So the most interesting question to enter into in the spaceflight environment regarding the nitrogen fixing symbiosis that plants form with certain types of microbe is how the lack of gravity would affect the calcium signaling that occurs between these two organisms. Calcium signaling is essentially like an oscillation of charge, like the electrical current going through your nervous system or the plants, and also the microbes. And so when the microbes first come in contact with the plants, there's a molecular dialogue that involves these calcium oscillations. Studies on plants and other animals in space have shown that these calcium oscillations are affected by gravity. So we're not sure exactly how the symbiosis relationship will occur in orbit. Will it be stronger? Will it be weaker? Will it be the same? It's a great mystery. That's one of the great things about space science. But one of the things we do know about this relationship is its fundamental importance to agriculture on Earth. Thousands of years ago, centuries ago, farmers realized you needed to do crop rotation systems and incorporated legumes to put nitrogen back into the earth. Since then, post-World War II, post the invention of the harbor process, that's the electrical system that humans generated to take nitrogen from its inert form out of the air and put it into a form which is biologically available. This harbor process revolutionized modern agriculture. It led to what we know as the Green Revolution. That's the intensification and mechanization of the agro ecosystem of the planet. This entire system is entirely dependent on two features: dwarf plants and artificially fixed nitrogen from the atmosphere. There's talk within research communities as how this could be done better in the future, because there's many positive and negative features associated with the modern industrial agro ecosystem. And many people think if we could push it back to a more natural agro ecosystem, this could be beneficial for the stability of these environments. And one of the things that would be like the holy grail of this system would be nitrogen fixing grasses, nitrogen fixing corn, nitrogen fixing wheat, nitrogen fixing barley. These are the major crops, these monocots, these grasses that provide the big cities with the nutrition they require for us all to have breakfast and all the other things that we enjoy. So in the future, there's going to be a greener revolution with the incorporation of grasses that have been adapted to form nitrogen fixing relationships with microbes in the same way that legumes easily, readily now. There's research ongoing in the UK and in America and all over the world into how to make this happen. And we can learn some great lessons from nature. one of the most interesting examples was discovered and published only just last year, which was this new variety of corn that's been discovered in Central America. It's giant. It gets like 3 stories tall. This thing is huge. And if you look at the internodes of corn where the leaves come out, what it's gone and done is produced these like little like rootoids. They're a bit like roots. I've invented a new word here, but they stick out in the air. And this area forms a slime. The plant excretes a sugary kind of mucilage. It rains quite a lot in this environment, and that's an important feature to make this relationship work. And then the free-living rhizobia in the atmosphere land on there and grow and fix nitrogen. And that's how these corn plants become massive. So moving that into other crop varieties that we use is going to lead to a really much greener agro-ecosystem in the future. And one of the ways we can speed that up is by understanding the conversation that happens, the molecular conversation that happens between the microbes and between the plants. And one of the wonderful ways to kind of unravel these networks is by changing them, is by perturbing them. And that's what spaceflight is. Removing gravity will change that conversation and will provide new insights as to how it works on a cellular, molecular, genetic, whole organ scale. But then it's up to other people to then take that information out into the field and see how can we use that to increase yield, increase sustainability of the global agro-ecosystems. But I haven't overthought it or anything.
That's absolutely awesome. You need to send a link on that 3-story tall corn with its little mucus sugary thing. I'm really fascinated about that mechanism because it's totally different than anything I've ever heard of before. So if you can send that, that's really awesome. You know, I'm realizing that we're running a little behind schedule, and I wanted to make sure that those that are tuning in understand a little bit more about Magnitude and our platform and what we're trying to do with the Leguminaut Challenge. And so if I can, I want to turn it over to Tony, our co-founder at Magnitude, to maybe do a brief overview of how to get started in the Leguminaut Challenge. It's really easy. And maybe just an intro on what you need to do to kind of get oriented. There are some lesson plans that are available online at no cost. This first phase of selecting our candidate to fly is absolutely free to anyone in the world. You don't even really need to have an internet connection. If you're a teacher and your students don't have it, maybe find a way to print some material out or what have you and get it to them. But it's help us find that next candidate to fly in February on our next mission. So that's one. And then we'll be following up with a second phase in which we're going to find the right material to grow our plants in. We're using an agar, kind of a gel, but is that the right medium to use? So Tony, do you want to walk us through the ExoLab?
Sure.
Or rather the Magnitude platform?
Okay, are you able to see my screen?
Yep.
Now, before I get started, I just wanted to let everyone know, if you are already a teacher or student on our platform, you don't need to sign up again. And you can join us with this Leguminaut Challenge at any time. Within your account, you are able to access that very, very easily, just going into the lessons library. Okay, so for someone who has not signed up yet, you go to our website, Magnitude.io, and all you have to do is you can either click here to get started to sign up, or if you want to learn more about what this challenge is, you click on that button. And this is where you can read more about it and all the previous conversation we had in the past, they are here. And our programming and our presentation by all the lagoon leaders, and you can find them here. And if you wanted to join us, all you have to do is click on this button, And you will be taken to this one screen to create your own account. For example, if you have a Google account already, all you have to do is click here. And it will ask you to sign up by using your school account or your personal Gmail account. If you have a Microsoft account, you just have to click on the Microsoft button. And this will, there are really only 3 steps to get your account created. Now, if you are not already a teacher, you create your own district, enter the name of your school, and also the email address. So I'm going to. So I'm getting this error because I am already a registered user. So all you have to do is click here, you log on, and you are seeing it, the dashboard of a teacher. Now, all you have to do is click on this button to see all the lessons for this Lumina challenge. Or you can always go to the menu bar to access that. And as a teacher, you can click to view all the lessons. And if you are coming from Germany, for example, you can click on this, select your language, to go to Dutch. And you will be presented with all the lessons in German or in Spanish or in French.
Oui.
Oui. Yeah. Oh, where are they? Okay. Yeah, so it is just that easy to get started. Take a look at all the lessons, and choose the lagoon that you think is best for the next experiment. And now, if you find yourself having problem getting started, you can email us by using this button right here. Need help? You can get a lot of additional information, or send us an email through here. Now, there's nothing for your student to do until you assign a lesson to your class. So the first thing you need to do is create a class first. So there are just only 2 fields. I'm not going to fill out another class. Once you have a class created, you are taken. You are being taken here to this page. Now, for your student to sign up to your class is really, really easy. All you have to do is share this link with them and the class code with them, and they will be able to create their own account under your class. Once they have the student account created, when they log on, they will get a blank dashboard. Now, that's why you really need to assign a class. Assign a lesson to the class. All you have to do is click here, assign it to your class, and select the class that you wanted to assign this to. That's all you have to do.
Wonderful. Thank you, Tony. Again, if you have a question, you can send it to hello@magnitude.io, or once you've logged in, that little blue button in the lower right-hand corner. Need help? It has most of the commonly asked questions answered there, but you can always reach out to us. And someone just popped up there's where our balloon is right now.
Yep.
That's pretty nice. So this morning at 8 o'clock Pacific time, about an hour and a half ago, we launched this from the just north of Berkeley on the edge of the San Francisco Bay. And what do you have there as far as altitude? We're about 1.5 miles up, maybe.
Altitude is 15,000 feet.
Yep, there you go. So almost, wow, my goodness, we're up there quite a way. It's on the way to 3 miles up. It's doing a little loop-de-loop, isn't it?
Yeah, it looks like it.
Really cool. All right, and thank you, Tony. I think we're kind of back on track now with our scheduling. Does anyone have any questions about the platform? Otherwise, I think we're going to be moving to our next segment, which is pretty fascinating. Dr. Barker is going to jump in again and share with us. And is Kai, has he joined us as well? Or will he?
He was planning on it.
Okay, well, he can pop in when he pops in. Well, we can roll with it. But why don't you go ahead and take the lead here, Dr. Barker? Give us a little background. And if I understand it correctly, we're going to be leading into a little bit of chemistry in the back end of what you're talking about, which would be kind of neat.
Indeed, yeah, okay. Share screen. So, so unfortunately, Kai isn't here right now. So instead, what's up? Back in the day.
Kai, what's up with the flashy gold watches, the freezer around your neck?
One sec, sorry.
Which I say.
So background to this, so Kai used to work in my laboratory. He was a research scientist, and he made some really wonderful discoveries about peroxidases operating in space, and how they help plants adapt to the stresses of spaceflight. And so after doing this research, he really wanted to help tell the story of the things he'd learned on the way. And so he has created a short series of videos on YouTube that are aimed at introducing students to some of the concepts that Astro Botany researchers investigate in the laboratories at the moment. And this is quite poignant because we're at the dawn of space agriculture. And so it's a really exciting moment to be a plant scientist, and we need lots of help. And the Leguminaut Challenge is a prime example of that. And so let's just have Kai introduce this segment before we talk about the journey to Mars and stuff like that.
You know, a lot of people have been asking me lately, Kai, what's up with the flashy gold watches, the freezer around your neck? Which I say, to quote the great Sheikh Zula, it's bling blong, baby. It represents my lifestyle as a street savvy, irreverent youth who lives large yet hungers for the next level in life. Welcome to the Astro Botany Show.
Young Mark Watney, study astrobotany. I make hanging gardens and nobody can stop me. Let's grow plants in space.
I'm your host, Kai Rasmussen, and today we'll be going over some of the basics of spaceflight plant biology. The first thing that I want to address here on the show is the history behind astrobotany. You'll often hear us refer to it as an emerging discipline or a new field, when in reality, this is only half true. Astrobotany has been around since the beginning of spaceflight, and we've been growing plants in space since as early as 1970 and 1980. But enough from me. Now we're going to head over to the history mobile. Alrighty, let's get right into it. In around the 1880s, some old head named Percy Gregg wrote Across the Zodiac, a big science fiction nerd story about a space traveler who went to Mars with plants. 15 years later, this guy named Constantine pretty much did the same thing, except it was a different book. And then let's fast forward to World War II here. And the Russian astronomer Gavril Adrianovich Tikhov was the first to define astrobotany and was appointed the head of the USSR sector of astrobotany. you're looking for more information about this guy, good luck, because I wrote his Wikipedia page. 1946, the first seeds were launched on V2 rockets. 1971, seeds were flown around the moon and called moon trees, even though they weren't actually from the moon. 1982, the Soviet cosmonauts grew a Thaliana on Salyut 7. They were the first to produce seeds and flower in space. So that's kind of a big milestone. 2016, the very beautiful zinnia flower bloomed aboard the International Space Station under the care of US astronaut Scott Kelly. And that is all she wrote.
Let's grow plants in space.
Oh, sorry, I didn't notice you there. Welcome to Item of the Week, where we go over an Astro Botany item of the week. This week's item is plant in petri dish, or if you want to get technical, this would be Columbia wild type of Arabidopsis thaliana in a 90 millimeter Falcon petri dish. Swear. The point that I want to drive home here is that when we're sending plants to space, it's typically not a house plant or in a pot or in soil or anything like that. We actually sow these very small research organisms onto a plate with media. The media is a secret family recipe of ours. It's got some salts in it, it's got some nutrients, it's got some sucrose in it, and it basically has everything the plant needs. You can see here, the plants are sowed on a clear media, and this media provides nutrients and also moisture that the plants need to successfully grow for maybe about 3 to 4 weeks until they get too big to be in the petri dish. Our media is a special type of media. It's a little bit harder than regular gel, and the reason why is because it needs to resist the rapid acceleration of launch. Wait, should I say anything else about it, or? See you next week.
I need to take a moment just to stop and thank my teachers, my professors, my coaches, my role models and leaders. Thank you to Simon and Richard, and big ups to NASA, to Wisconsin, my school home, and soon on the map.
Well, it's virtual Kai, so that's the next best thing, I guess.
Yeah, like
The meta.
But like, so I think that's a really great introduction to kind of where we're at. Like, as a research scientist, Arabidopsis thaliana is my favorite tool for understanding how life responds to the spaceflight environment. But like, we have to understand the past so we can know where we're going, right? So if Kai turns up, if you let him into the room, just poke me, because if not, I'll just freestyle in the meantime.
Okay.
So we have to know the past to know where we're going. And so we're going to go on a storyboard. We're going to go through on a journey to Mars. And along that way, we're going to encounter some like scientific hurdles. And we're going to have discussions about them because this is all freestyle, right? So one of the key things, one of the themes to this is going to be salt. A bit later on, there's going to be an educator who's going to come and talk about some of the ways that we can use salt from your kitchen to help students, like right now at home, practice some really important laboratory techniques, things that all the molecular biology industries use to this day, such about dilutions and molarity and dissolving, things that happen when you dissolve salts in water. And she'll go into all that kind of technical kind of thing later. But why is salt important? It doesn't, surely its only role in life is to make a salad taste nice. But it's actually more important than that. It's been historically, it's been revolutionary in many parts of the world. Like,
it does make a salad taste nice, but stop calling me Shirley.
So in the past, I meant to get some slide for this, but I didn't. In the past, there was this moment when Rome like expanded across Europe and this empire like dominated the Mediterranean region. And then there's a moment when Carthage, a rival empire, like attacked their capital and sacked it, and they were decimated. And then Rome, like generations later, were so angry about what had happened. They went to Carthage, they destroyed the city, and then the historians wrote they sowed the fields with salt. So they added salt to the fields, the agro ecosystem of that surrounded Carthage itself, so that no longer in the future could a civilization rise up there to challenge the might of Rome. So even back then, 2,000 years ago-ish, humanity knew that having salt in your field is pretty bad. And so that's the past. Time has come forth. The Green Revolution has occurred, and we live in a really wonderful time as humans go out into space. And so that lesson from the past may come up and inform some of the issues we may have in the future. So let's just kind of have that as our foundation as we start to imagine a journey to Mars. So the journey to Mars. So I'm a big fan of computer games. I think you can learn a lot from computer games. I'm a big fan of modeling. So back in the 90s, one of my professors gave me an opportunity to do some modeling of the climate, and we predicted certain climate change patterns. And it was interesting to see many of those things actually happening over the following decades. So ever since then, I've been intrigued by the power of modeling. But also some of those old models were kind of scary because they're, and so I realized there are some models out there that are less scary, but are equally informative. And so there's a computer game that it's called Terra Genesis. If you're going to play it, the trick to it is to avoid the adverts. I'm sorry, it's free, but there are some adverts hidden in there, but they're just advertising other games. So don't be distracted by the opportunities to invade your neighbors and those types of things. Stay focused on terraforming Mars. It takes many weeks to do, and it's one of those things that shows that interesting things in life don't happen quickly. Not all games are meant to give you that instant satisfaction of like winning immediately. A lot of the greatest challenges take a long time to manifest. And I'm going to take you on a journey that took me 3 weeks, which was the terraforming of Mars in the computer game. Along the way, we're going to encounter some real science, which is kind of fun. Okay, so, and I think this is a great transition from the work earlier that you were talking about with the high altitude balloons, because those things, they can produce data and they can produce art. And these two things are not mutually exclusive. And so the computer game that I was playing is a kind of an artistic interpretation of the future, but within it, there's science and there's lessons to be had. And just as with this picture of a bonsai tree flying above the curvature of the earth is just a beautiful piece of art, within it too, there are like reflections of science that we can like learn from. On the picture on the right, the past, present, and future, this is just an image I found on the internet. So what's the lesson here? Be careful what you see on the internet. Like, for example, 100,000 years later, Mars being terraformed like that, maybe that's impossible. So maybe there's people writing things on the internet that are not true. But maybe if we work at it and we all have a collective vision, maybe that could become true, or a variant on that. So again, we're trying to create students that are inquisitive and don't just believe what they're told. So if at any point during this conversation, something comes up that you don't believe, write it down, find it an intelligent way to create a question to challenge that assertion. Because there's going to be a lot of misinformation, because the internet is a source of all the information. Everything you can imagine is there. And so some people imagine incorrect things. But if we imagine stuff together and we check each other's imagination, eventually we can find like a true, real summary of what reality is.
A good point. Dr. Barker, can you make a full screen of your presentation?
Oh, sure, yeah. I have, I forget there's like everyone's faces at the top, so it's kind of not hidden. Okay, so so this is a journey into the future. We started off with the past. Whoops, participant thing there. There we go. So why are we going on this journey? Well, we have to, like NASA's making, it's our job for NASA to go on this journey mentally. So that way we can develop the technologies that will prepare and help the astronauts overcome these challenges. So this is like the greatest journey that humanity is ever going to go on. Like there were moments when humans explored the Earth, which were tremendous. But this next voyage of exploration is going to take us off the cradle of humanity, like our blue origins, planet Earth. So where are humans going and how can we help? Because it's all very good and well to know NASA sending some astronauts off on this journey, but a lot of us want to help. And we don't want this journey just to be like a waste of time. We want to learn things on the way and make sure that they help us here on Earth. And so I'm going to show in this presentation, hopefully, a way that everyone can help for when those astronauts get there. And that's going to lead into Christine's lesson later. And that's also, we're also going to reflect about how that can help us here on Earth in the future as if the United Nations models pan out as we predict, but so we'll come back to that later. So, okay, where are we now? We're here, we're at the International Space Station, we're on planet Earth, we're in low Earth orbit. Humans have sent satellites to Mars, we've gone past Phobos and Dios, the moons. We've landed robots that are driving around. Oh my golly gosh, what an exciting time, right? And soon we'll be sending helicopters over there. So we're going to see more of the Martian surface at a closer resolution than we ever have before. And then humans are going to land on the moon. We're going to have a moon base. And why do we need a moon base? So the moon base will help launch us on the way to Mars. There's many potential strategies for going to Mars. You can go Mars direct. That's some of the way that SpaceX wants to go. But there's a more like prudent step-by-step mechanism, like a hopping from stone to stone, if you will, approach, which was first postulated by von Braun, like the father of modern rocket science. And he believed we should have a moon base to launch us onto Mars. If we get there, we have to imagine a future that could occur on the planet. And so this is where that computer game I mentioned came in. So I've been playing this Mars Theogenesis, and you can see here, this is the terraforming steps. So planetary ecosystem synthesis is a concept that was first written about in the University of Wisconsin-Madison about 10 years ago as by an ecological professor who wanted to teach about modern succession on Earth, and essentially applied all we know about succession on Earth to Mars, and basically defined how we would need to change the Martian surface in order to cause succession to occur there in a way that it would here on Earth. By succession, I mean the growth of like microorganisms, bacteria, algae, eventually mosses allowing the primitive ferns and such, and then eventually maybe even animals. And so it's a bit like going up a mountain. It's the higher up the mountain you go, the less life you get because of the more inhospitable it becomes. So Mars is the top of Mount Everest. So if we can push the characteristics of Mars down to lower altitudes, then eventually life could live there. And it did once upon a time. If we go back to billions of years, Mars was once a very wet planet, just like Earth is now. It just doesn't have a big iron core, so it doesn't have a big powerful magnetosphere around it, deflecting the solar winds. So the water and other like ions were stripped by the solar winds, and Mars has been left pretty barren looking today, and then been baked with UV radiation. So there's probably not a lot alive on the surface, but we don't know about deeper down. And that's why it's such an exciting concept to have humans go there. So, okay, let's imagine moving forwards, we can terraform Mars. We're going to come up with some superstar, a Groot, if you will, by gamma irradiating plants like Arabidopsis thaliana. We'll create new mutant varieties that are resistant to some of these stresses and would just bend the laws of reality to make it happen quickly for the sake of this storyboard. But essentially, if enough people imagine the storyboard, there's no reason to think we couldn't come up with the technologies to overcome all of the various hurdles. So Artemis, Project Artemis, that's code word for going back to the moon. Everyone's heard of the Apollo, when man went to the moon the first time, the greatest camping trip humanity has ever been on. And we're just on the verge of the next greatest camping trip, which is Project Artemis. We're going to send the next man and the first woman to the moon within the decade. Unfortunately, COVID-19 might have slowed that down a bit. We were aiming for within 4 years, but there's a lot of, it slowed us down a bit because we can't move around to prepare some of the rockets and infrastructure. But this is an international effort. There's various different aerospace companies that are offering delivery services, SpaceX and Blue Origin being the two main competitors, but there are other people in the area. The European Space Agency has a plan to 3D print some moon bases. The Chinese Space Agency equally has strategies to build chambers in which they will be developing bioregenerative life support systems. That's pre-designed ecosystems that provide all of the water and nutrients that the things living in it need. And they've been testing that on Earth. Viva the biodome. And then eventually, once this moon base has grown, the city will probably be known as Artemis. And this was based on recent science fiction. There's a lovely book about the first lunar city, Artemis. And once that gets big enough, that will then enable the lunar mining to produce the rocket fuel for the next great trip, to take humanity from our blue origins, the cradle of humanity, onto Mars and elsewhere in the solar system. Doesn't the Earth look beautiful from up here on the moon?
Hey, that book you mentioned, Artemis, that's by Andy Weir, the same author of The Martian. So if you saw the movie or read the book, that's actually a good story there on the first settlement on the surface of the moon and how they want their own liberty.
Mm-hmm. And we'll come back to the political conversation about as humans spread across the solar system a little bit later, as we refer to some other poignant science fiction literature that should really be on every student's reading list for this quarantine period.
The Foundation?
Yeah.
Or is that a little too extended?
Maybe. This one's called Red Mars. The movie is terrible, but the book is awesome. Anyway. Okay, cool. So everyone agrees having humans living on the moon would just be awesome. Could you imagine that? The Lunar Olympics? I go on about it all the time. We have the normal terrestrial Olympics, we have the Winter Olympics, and then we have the Lunar Olympics. And then we have a economy operating in space. So we're not just relying on NASA to get us to the moon. NASA is meant to push the boundaries. They're not the taxi driver. They're the person that allows us to go beyond what was done before. So that's why it's so important to have private economies working in low Earth orbit, in cislunar space. So that way NASA can push the boundaries and go beyond to the red planet. And could you imagine a 9-month journey all the way to Mars? Bloody hell. Oh dear, that would be terrible, wouldn't it? You'd get so bored. And so what would you do to keep yourself sane? I know this is the case because I'm in quarantine at the moment. And if I wasn't able to go into my garden and nurture my plants, or did I say more importantly, go into my basement and monitor the plants I'm keeping alive indoors in my urban environment, in my built environment, if I wasn't able to do that, I would be going stir crazy. And I know this because I have a friend who's currently in a small studio flat who can't go out because of quarantine, and he is going stir crazy. And it's not just anecdotal stories like these. Roscosmos has done studies where they've sent cosmonauts into isolated places in the Siberia, and shown that if you go there by yourself, you go crazy. And then they sent 2 people to go alone to Siberia, to this remote place by themselves. Can you guess what happened? Yeah, they went crazy too. Then they sent 3 people, and they gave them some plants to look after. And these people came back and they enjoyed themselves. And for me, though, as a scientist, I break down. What did they do wrong? They went 1 person, 2 person, 3 people, and plants. So they changed 2 variables. So do you need 3 people or more, or do you need plants there to keep you sane? Well, I'm going to bet on the plants because I'm a plantophile. And wouldn't it be great if you're flying for 9 months on a journey to Mars, if you could grow some plants with you, just to keep yourself sane? Not to mention the nutritional benefit they provide if you eat them. So what happened when you get there? Soft landing, we hope. Cold reception, definitely. Yeah, Mars is a cold, barren place. They've recently been filming for the new June movie that's coming out, and they were doing it in the some of the Arabian deserts, and those places get real cold at night. And so we'll be staying indoors, and we're going to have to completely rethink the way we think about time. And this will be really hard to begin with, because we have a diurnal circadian rhythm that keeps us going. And that circadian rhythm is partly genetic, but also partly environment. So the day-night cycles also help maintain your circadian rhythm. So when we get to Mars, we have altered day-night cycles, we have altered day lengths. It is going to play with our minds a little bit, but humans can adapt. They can overcome those challenges. So I have a new calendar, just like we went from AD to BC, and it'll be the Martian calendar. And that will help account for the longer Martian days and the longer Martian years.
What will your watch face look like?
Well, that's an interesting question, because so their day was like half an hour to an hour longer. I think it's half an hour, something like that. So many people have postulated that humans will just stop the clocks at midnight. Their hand will pause, the half hour will pass, and then the clock will start again. I don't know, but that's a great question. Again, that's one of the things explored in the book Red Mars and the trilogy that goes with that. It's really cool. Okay, cool. So in this game I mentioned, as I was starting, the people have just arrived, just at the beginning. So what's happening? So this is 2036 in my game, so a little bit in the future. I've called my pioneers the Daughters of Gaia, because that's cool. And we sent 170 people on the first ship to get there, because we didn't want small numbers, because we didn't want to go crazy. It's too cold and there's no air pressure outside. There's not enough oxygen. It's a bad place to be on the surface of Mars right now. So what do? We do what all mammals do, we go underground. You know, like the dinosaurs used to be the biggest and dominant species on the planet. Do you know where mammals are now? Any takers from? It's a cool, well, it's kind of scary concept though. Asteroids, right? Like, but why not mammals? Why was that not so bad for mammals? Because we emerged from that much better. It's because we live underground. Well, at least historically, look at mice in the wild. Look at all these other mammals. Like, there's a lot of them that dig underground. It's those early mammals that eventually evolved out to become us, had a habitat which was more stable because they were living in holes under the ground as the planet changed around them as a result of that massive meteorite impacting. So when we go out into the universe, maybe we should reflect, look back at what happened in the past and think, what traits will a mammal exploring space in the future have? And maybe one of those is living underground, at least to begin with. But plants, we want plants to go with us, right? And what do plants need? They need a few things. Oh no, there's a clue on the screen. Okay, water. Damn, that didn't work, did it? They need water. And so this image has been provided by NASA. It shows their proposed landing site. And this has been, there's been there's been an international consortium of scientists that have met regularly, and this is the region they've defined. And this is based on some NASA-like satellite data, which shows water underground, or ice water underground in the northern pole. You can see right on the top, what do you see there, that white stuff? You can guess what that is, right? Yeah, it's a massive ice deposit, but not just like...
Yeah, do have a question from one of our students in South Africa, Melissa. She asked, with Mars being very cold, the temperature is too cold for humans to bear. So if we plan to live on Mars, how would we increase the average temperature to be suitable for humans and plants?
That's a great question, and that's one of the things we're going to. So at the moment, we're living in built environments. We're living in habitats that have got like awesome insulation, and inside, I would bet they'll be using nuclear power plants, nuclear generators, ideally fusion. A lot of people believe we'll crack fusion within the next 10, 20 years. And if not, it'll be fission. I know there's a lot of concern about sending nuclear fuel into space, but the deepest probe gone out into the edge of the solar system was powered by a nuclear isotope that was decaying. So we shouldn't necessarily be too scared of technology like nuclear power. We just need to understand it better to make sure that we use it carefully. Yeah, so probably nuclear fuel will be generating the heat that we need internally, and then advanced insulation systems will allow us to build domes underground, and then we use the bedrock itself also as further insulation. But there'll be other ways we can heat up the planet, and so this initial part of it will be all underground with water, because more supplies will come from Earth. So we've got our first little 170 people dug underground, and they're gonna guess what's in that box? It's the nuclear fuel that we need to keep our place warm. So underground in these built environments, we'll be growing our crops in these hydroponic systems and living underground. And there'll be a small network that starts to grow. Well, at least that's what the model showed. And the model I'm referring to is that computer game I was playing. So it's funny that this computer game was also reflecting the same story that occurred in Red Mars, the science fiction novels that I alluded to earlier. And it could be the next book in the series of The Martian. I'm not sure if there's any books that are going to follow that one, but so underground network. But eventually,
we have another question there.
Great, fantastic.
Well, from Ludovico is asking, if we do grow plants on Mars successfully, there are still some constraints like the massive sandstorm and earthquakes on Mars. So how will we be able to protect those plants? And I guess in a very similar way, the way you're talking about protecting us from the cold, going underground or what have you. And that illustration you've got on the screen right now might answer some of that as well.
Well, exactly that. So the sandstorms are actually really mild. I mean, there's some where it looks really big and covers huge areas, but the atmosphere is only about 1% of that of ours. And so, like, for example, the beginning of The Martian, there's an impossible thing that occurs, a windstorm that like destroys their base. The wind could not be that bad because it can't be that dense unless we as a species went there and implemented planetary changes. A lot of people say that's crazy, but as humanity grew on Earth, we have created planetary changes in different regions, and we have been able to monitor that with modern science and technology. And so to think that if we got enough humans up there that we wouldn't start to change the environment on Mars is a bit crazy. But anyway, I digress. So yes, very good questions, very good questions. The atmosphere density is a really important feature that you're getting to, the storms up there. And earthquakes, actually Mars is relatively tectonically inactive. It does have a few tremors here and there. And it was actually a really exciting moment like earlier this year when a Mars lander was able to detect the first Mars quake. But it was relatively mild compared to the ones that we experienced, or you guys experienced in LA. So one of the reasons for this is the really interesting geological occurrence that's happened on Mars. So because of the rate at which it cooled, it basically formed a giant volcano, Mount Olympus, if you will, Olympus Mons, as we call it. It's the biggest volcano in the solar system. It's huge. And would be a pretty cool place to build a city if you were playing a computer game that allowed you to terraform Mars. Okay, cool. So our civilization currently is underground, but we want to move out to the surface. It's inevitable. We want to look at the sky. It's in our nature. My favorite color is that shade of blue. You know, not just any sky blue. It's got to be a spring day. You're lying down in the grass. You've got like the stream running by. You're looking up. There's not a cloud in the sky. The center of the sky there, that shade of blue is my favorite color, my favorite shade of blue. And so humans love to look at the sky. There's something special about that. And so we won't want to remain underground for long. And we will be developing technologies in order to enable us to go onto the surface. One of the major issues about going onto the surface is the amount of UV radiation that the planet is bombarded by. Without the magnetosphere to deflect this radiation, and without an atmosphere to absorb some of this radiation, we would tan real quick. And this UV radiation is also detrimental to plants. It damages their DNA. Some plants are adapted to this more and some less. And so over the coming years, humanity will be finding out the genes are involved in resistance to UV radiation. And we could essentially create a synthetic program where we design plants to use that radiation for making sugars. And this all may sound like crazy, but this is the painting that's been pictured by sci-fi writers for decades and decades. And one of the great things about it is this picture has a guy in it, a person right there in the middle. That's a friend of mine, Ray Wheeler. He's a Astro Botany researcher at NASA, at the Kennedy Space Center. And he has been investigating how to grow plants in spaceflight environments for decades and decades. He's a pioneer in the area. And has developed many of the technologies that will enable us to grow huge amounts of food in confined spaces and in extraterrestrial environments. So hopefully some of the students who get excited by this will one day be continuing the work that he started now. But we're going to need more water on Mars. So there's some, in the science fiction, there's just loads of water under the ground, and the satellite images from NASA do show there is water under the ground, but like not loads, not as much as we need. Humans are greedy, you know, we're going to want to use, we're going to want to grow there, we're going to want to build a lot of biomass up there, and water is an essential building block of our biomass. So in some of these science fiction novels, one of the ways this is achieved, and in the computer game I was playing, is that you can slam asteroids into the planet. So many asteroids have got lots of water and nutrients. There's like an interesting theory about the origins of life on this planet potentially being from an asteroid impact, a bit like this. Jury will always be out on that.
Now, Musk actually had this proposal at one point, didn't he?
Yeah, he has joked about this, and he has also joked about sending other, what's it called, nuclear rockets into the planet. Yeah, so there's another great game. It's called Terraforming Mars. It's a board game. I think it's really good. I've been playing it lots recently because there's.
Can you do that over Skype or Zoom? That's
I was actually about to reference, like, when you talked about crashing the asteroids into the surface. I was like, is that from the game Terraforming Mars? One of my favorite dice games. Yeah,
it's really good, isn't it?
It's so good. For those of you that don't know, it's essentially where you play as a corporation that has to attempt to terraform Mars. And you're given 6 different types of resources you have to use. You have to use plants, energy, heat, steel, and then the actual credits your corporation has. And I think science fiction is so important because the thing about science fiction is it's grounded in reality. So all the questions that you ask in that board game, you know, how do we introduce animals onto Mars? How do we introduce life? How do we look at all these things and manage our resources to do it? I think it's really cool.
Oh, there you go. I've got that on my game list now.
Yeah.
But can we play that via Zoom or Skype? That's the question.
Oh, I actually need to check that out because I've really been enjoying Dr. Barker's discussion on science fiction here, because that's where I started from everything. I can literally go underneath my shelf here. I can pull out copies of Dune and Asimov and everything, because that's a big obsession of mine. So pretty cool.
Shivar, my friend,
yes.
Make sure you could I get your email? I'd love to share this presentation with you and request that you put in concepts from that game. You know, they have like the they have like the images that go with the way the card that you play changes the game.
Yes, it actually changes it. That's why no game's the same, essentially. So
between each of these slides that I've gone through, you could imagine some of those game cards going down, right?
Yes, exactly. That's exactly what I've been imagining now through this whole talk. So yeah.
I'll send you the link, and then if you could actually put those in, I would really appreciate it. We could have a conversation about that, and I'm sure it'll be a great way for other teachers to use this story to help it grow.
I'd absolutely love to. No, definitely.
Guys, I just found on the Apple Store that Terraforming Mars is also available as a digital app for computers, phones, tablets, gerbils with computers on them. It's there.
I love it. You guys are geeking out. This is great.
It's a fantastic game.
Anyway. Yeah, it's great.
It's really good, right? And so in order to get to the next stage of Theogenesis, I needed water, and the game just allows you to make water by building buildings and stuff. But in reality, you can't just make matter out of nothing. We're going to need more water. So this storyboard just quickly added in, we're going to crash in some asteroids that are loaded with water, loaded with ice, because they're up there, you know. And actually, that's one of the great things about Mars. It's actually really close to the asteroid belt. So a lot of people think that one of the great things about it is you could use it as a stepping point to go and start to mine the asteroids. A lot of people also say you can just skip that and just go straight to the belt. And that's the foundation of, what's that Jeff Bezos' series? It's on Netflix.
It's The Expanse.
The Expanse.
Yeah.
You got it. Another brilliant series. If you haven't seen it, you really must watch it.
Unbelievable.
Oh, I haven't read the books, unfortunately, for that one, but I need to.
Please, you have to.
But again, these are all like science fiction writers that are painting the picture. So this is a great thing about STEAM. Like you have to have the scientists, you have to do the experiments, but they need to be inspired to do the experiments by the artists who like think beyond what is currently feasible to inspire us to go beyond, right? And so to go beyond this part of the storyboard, we got to crash some asteroids into Mars and add some more water to it. And in this particular version, it's going to cause controversy across the solar system, because no matter what, you're going to have some people who think it's a good idea, you have some people who think it's a bad idea. It's just the nature of humanity. And this is explored beautifully in the Red Mars, Green Mars, Blue Mars trilogy, as they talk about the first 100 people that go and the colonies that forms and the way all the politics unfold. It totally reflects on the way politics has unfolded over the last 200 years and puts that into the Martian context. Humanity intrinsically divides itself down the middle. Anyway, so again, great book, great reading, awesome. So we've added water, yay! So we can get gases. So we can go to the next stage of getting more people there, and they're going to bring more resources. They're going to make more heat. And see this positive feedback loop. That's what humans build. When they go to places, there's a certain characteristic, and they provide a positive feedback loop to enhance that characteristic. Sometimes that's detrimental to the local ecosystem. Sometimes it can be beneficial. So it takes a couple of horticulturists, a couple of gardeners. They go to like a tropical paradise. What they do, they build a botanical garden and they try and make everything healthier and happier and collaborate with each other. Or you have a couple of like logsmen that go there and cut the lot down and sell the wood. So like, this is that duality that exists within humanity. And in theory, with enough humanity put into education, we can overcome that duality and make sure that we act like the shepherds of nature that we're meant to be. So now we have our terraform planet and we have more water on the surface, and we've started to raise the temperature a bit. So some of those aquifers underground have started to melt. Our civilization is growing across we're getting connected. We're mining out other like things that we need to continue to grow as a economy, but we're limited. Just like the ancient civilizations before, we're limited, and the future and the same thing that's going to limit the future of humanity, and this is souls. The industrialization, the green revolution, which is the industrialization, mechanization, and intensification of modern agriculture, has led to the use of inorganic fertilizers. We spray a lot of nitrogen onto the fields, which is great for yields. We love it. I do love cheap bread. I really do. And allows me to do a lot of other things during my day. I don't have to worry about eating, so I can think about going to Mars. So having access to this supply of cheap food is really good for humanity. But unfortunately, there's a byproduct. And there is data to show that the gradual slow increase in salt in agro-ecosystems around the world. And if this continues, we will see what happened on Mars happen here, the desertification and salinization of a planet. So we need to adapt the way our agro-ecosystems functions within the next century. And interestingly,
yeah, is that true that we've got essentially 30 to 60 years of topsoil based on those calculations?
Yeah.
Yeah, so it's a real challenge here that what we're doing here as we begin investigating these legumes as a potential solution. It is a real world problem.
And that makes me remember a Astro Botany TV show episode. Can I pivot? No, then I'll come back to this story. Hey, why not?
Yeah, time check. So 15, and then Christine, I think Hurst has joined us, so we can kind of segue into chemistry over the next 15 minutes or so.
Absolutely perfect. Hi, Christine. And this was just as we discussed. You can see how we're coming into salt as we were discussing. So I've got to find the Astro Botany TV episode I'm after, which is not the history. So it's almost like I hadn't planned this bit, and I've just remembered something, and I'm pivoting sideways.
You know, a lot of people have been
pause. Where is there? Should be a link to the channel, shouldn't there? Where's the channel? Does anyone know how to work YouTube?
as you locate that, there's some questions here, interesting questions about energy. It'll take us a little off topic, but I just want to acknowledge it that we're thinking about, Ludovico talks about putting a giant mirror out there to reflect sunlight to melt the ice caps, to try to form an atmosphere. Pilot Flood asked what types of energy could be used on Mars, except the obvious of solar. And I think Dr. Barker, you'd mentioned nuclear. And then the idea, of course, as you'd mentioned, with the asteroid belt as a mining or refueling station, which I think is a good point, Christian. So did you find
Nearly
If I could just jump in here for a second while he's looking at that. One of my graduate school classes that I'm taking is on closed systems, and that means using more in situ resources, including the regolith on Mars. And NASA has already been experimenting with a variety of mining type of technologies and life support system technologies. Some would just be reducing or processing the carbon dioxide, because that's CO2, right? And if you can process it, you can get oxygen from it and then have a byproduct as carbon. Or processing the CO2 and water from the soil to produce both oxygen and methane. But they did one study where it looked at the amount of water concentration in the regolith, and there were concentrations of like 3%, 5%, 8%. And the concept was if they went around the areas of Olympus.
Oh, no, this is
yeah, it's like, stay tuned for the next episode of
oh, so there's a position somewhere out there. That's awesome.
Yeah, Laura will pop back.
Poles, you could be along that more equatorial region and come up with enough water. But there's a variety of physical chemical systems that NASA has already started researching and playing around with a bit.
Lori's connection's like mine, intermittent.
Well, and going on that, so NASA are really aware of a lot of the constraints of the agro-ecosystems on Mars, and started thinking about how they would build that biogenerative life support system. So about that, you cut out, so I'm just kind of riffing off it. And this is a great example of that. So I'm part of the NASA Gene Lab working group that's investigating plant response to spaceflight in extraterrestrial environments. And online, NASA deposited the data for an experiment that looks into plant response to magnesium sulfate in hydroponic systems. So when you build your first and Laurie knows about this because she's got a fantastic hydroponic system at home on her balcony area. Look at that, perfect, right? You saw that in the background. And so what they've done is they've actually pre-prepared that if you have hydroponics running regularly over a long period of time, unless you're really good at cleaning them, you get these little salt crystals that build up in little places. You want to get rid of them because eventually the salt will get to a level that'll stop your plants from growing, and you'll start to lose yield. If any of you want to look into the genetic response to that and how we might be able to genetically engineer resistant plants to that, these data are on the NASA Gene Lab repository. They're also on my website, Astro Biology. And let me show you that, because this will have a real physiological impact. So what happens when salt starts to build up in an ecosystem? That's a good question. I'm glad you asked that. So I'm going to look at the plants and salt data that I've been gathering over the years. Okay, so plants are sensitive to salt. I'm going to make this big. So what we're going to see here is genetic data that shows the plant's nervous system. We're going to look down here. You can see that red comes through and then up. So what we've done is we've added salt to the end of the root tip here, and we've looked at an electrical wave, a calcium wave, a wave of reactant oxygen species that's moving through the plant. Just like when you touch your finger, you feel that wave going from your finger up to your brain. This is the plant version detecting salt being added to its root tip. And why does it detect that, and why does it transmit that signal? And well, it's because it wants to adapt. The plant wants to survive. You can see this picture, green picture here in the center.
That's the nervous system in the leaf that then interprets that signal. So the plant can adapt to the salt in its environment. And so we have what we call natural variation in sensitivity to salt and response to salt. So you can see this interface just here. This is an experiment I did a few years ago when I was an undergraduate. So this is why students, you guys are young researchers. Don't think of yourself as being anything other than that, really. I created this study when I was an undergraduate at University of Nottingham. So Arabidopsis is my favorite plant. I've mentioned it before. And there's over like 1,300 versions of it from all over the world. Scientists have collected them together. And I was able to get my hands on a collection of 100. And so that was really cool. 100 little tubes of seeds. And you can see these dots here. This represents where those seeds originally came from. And what I did was I grew them on salt and I grew them on media without salt. And then I measured their growth. And you can see that some of the varieties, they grew really well. So these European varieties here, they evolved in kind of salty environments. And so they grew really, really well. But some of them didn't grow well. Some of those varieties were really sensitive. So within any species, there's natural variation, right? And so there's going to be natural variation to something like salinity. So we can then investigate those resistant varieties wherever they may have come from. So there's 3 of them that came from Sweden. And we can then start to work out why they're resistant and ask ourselves the question, can we use that to ensure that salinity isn't an issue in the future of agriculture on Earth? And the most resistant variety comes from America. Oh, I didn't even realize that. Anyhow, so natural resistance to salinity. The other thing I'd like to say is there's 2 different characteristics that I was measuring. I was measuring the shoots, so the size of the leaves, and I was measuring the size of the roots. And so I was measuring, and we can use that to interpret the signaling that occurs between the roots and the shoots. So the moral of the story is salt is an issue for the future of our agro-ecosystems, but that's not despair. We can come up with a solution if we work together, if we plan ahead, if we believe the data, and if we act on it. And not only will that data help us ensure that we have a sustainable agro-ecosystem here on Earth, it will also help us go to other planets, such as Mars. Hang on a sec, this bloody thing's full screen and I can't get out of it, it's full screen. And so this leads us to one last project I'd like to briefly show, which
my name is...
Oh, I thought I had it. Where did it go? I totally
How
had
many
it.
tabs?
Typical. Joanne Co. Okay, one sec. Sorry. It was in the other one, wasn't it? Here it is. Found it. I shared the wrong screen, cause that's life. You can never too old to learn. Right. Okay. Can you see this thing screen that's loading?
Nope, you haven't shared again.
Okay, cool.
Hey guys, what's going on?
Pause.
The voice of Kai.
Yeah, he tells the story well. Okay, and so this salinity issue is not just important to me, it's important, I try to make it clear it's important for everyone. And so Target got really interested in that, and they've created the Cotton Sustainability Challenge. And so we took part in this, and this is going to lead to an experiment on the space station, which investigates plant response to spaceflight, but with a very special variety of cotton that's been made resistant to salt. And so with that kind of premise, we're going to do list to see what happened in the interview.
Hey guys, what's going on?
Because I forget.
Today we're going to be talking about what is this? Is this cotton? Where's it coming from? Space?
Young Mark Watney, study Astro Botany. I make hanging gardens and nobody can stop me. Let's grow plants in space.
So today I've asked my mentors, Dr. Simon Gilroy, welcome back, and Dr. Richard Barker, hello, to discuss the opportunity that they recently received to grow cotton in space?
So the project is led by a government entity called CASES, the Center for the Advancement of Science in Space. Okay. They're all acronyms. And then the sponsor, who's actually bankrolling and making that part of it happen, is Target.
Oh, okay. Cool.
And so one of the reasons to want to do the spaceflight stuff is to try and learn enough about cotton to work out maybe how we could grow it a little bit better. Cotton is a hugely thirsty crop. It uses tons of water. And because it's such a important business, it's very intensive on agrochemicals in a lot of settings. And those two things together make cotton have a big impact on the environment.
Richard, I found this on your desk. Do you mind explaining to me what is this thing, Richard?
Sure.
What is this?
So this is actually a piece of NASA certified spaceflight hardware. We're now going to use this to grow some of these cotton seeds on orbit. We'll have some of these, the same hardware, have it growing on Earth at the Kennedy Space Center, and we'll be able to compare the plants that grow in this on Earth to those that grow in one of these on the space station. It's a simple device. The best thing about it is it keeps the microbes outside, so inside is completely sterile. And has a custom adapter on the bottom that allows the astronauts to inject water, which will cause these seeds to germinate. The shoots will then go up towards the light above them, and the roots, well, we just don't know. We'll have to wait and see.
Let's grow plants in space.
I love the documentary The Martian. Have you seen it?
The documentary?
It's brilliant. In it, a character called Mark Watney ends up growing some potatoes on Mars using his poo and Martian soil, Martian megalith. And for me, this is one of the moments when the science kind of breaks down in the movie. On the whole, it's very good, but this one moment, he does not wash the soil. He just uses the Martian regolith straight off the ground. Whereas we know that Mars has dried out on a global scale and has got a thin layer of crust over a thin crust of salt over the surface. And so that soil would not allow him to grow those potatoes. It would kill the potatoes. So interestingly, the technology that we're going to be using that's inside these cotton seeds actually allows these plants to grow well in salty soil. It actually allows them to produce a high yield, a sustainable yield in salty environments and drought environments and dry environments. So we are intrigued and excited to learn how this technology will allow or help adapt plants to growth on the International Space Station and maybe even eventually on Mars.
So Simon, Richard, thank you very much for coming in to talk about the experiment. I hope you guys keep us updated on the progress.
Absolutely.
Let's grow cotton in space.
I need to take a moment just to stop and thank my teachers, my professors.
Like, comment, and subscribe. And if you want to support your local astrobotanist, you can pick up one of these cool Astro Botany shirts at astrobotany.com.
Hey, Richard.
Hey, guy. Yo. How's it going? Far away. Oh, you got your t-shirt on.
Just saying, the stuff that Kai made is pretty rad. I should pick one of these up.
So tell the story of how we met, my friend.
Yeah, so I was developing. I run a Astro Botany research and education program in Japan, and I was looking for some expert help because you need expert help when you try to do this kind of stuff. And as I was looking online, I was looking for resources in Japan, and then I found Kai's channel. And I saw the very first episode that you guys saw, and I was cracking up. And I'm like, who is this guy? Like, this is hilarious. And then I looked up Richard and Dr. Gilroy. I'm like, who are these guys? I sent Kai a message telling him what I was doing and to see if he had any connections to anyone he knew that could kind of give us some insight and direction. And then he connected me to Dr. Gilroy, and Dr. Gilroy to Dr. Barker. And then it just blossomed into this awesome fun collaborative relationship, and they've sent stuff over to Japan. We've sent stuff over there, and I got to meet Dr. Gilroy for the first time over at Kennedy Space Center, and then Richard and I were presenting at SEEK last February. So it's been really cool. So yeah.
So this is one of the wonderful things about Astro Botany. It's difficult and it unites the world. We all want to work together to make sure that we can achieve these lofty ideals as a planet, as humans working as one. And so this is the moment where we pivot to like what we really need the students to be doing and the skills that they need to be practicing in order to ensure that we can do these challenges, overcome these tackles. And this is one of the great things, like, because I think Gil was doing some salinity investigations with his students last semester. Did they enjoy it?
I'm sorry, what was the last thing you asked?
Did they enjoy it?
Oh, they loved it. They loved it. It was really frustrating at first for them because everything just died. And I was like, great, you have a room full of death. Continue exploring. And they love it. They still have problems with the salt. And another problem we have with regolith is cementing. But they're loving it, yeah.
And so that's why I assume Christine is here, but that's why one of the things that we like to practice is what we call concentration gradients. So if you just go to a really high concentration of salt, you will just kill all of your plants instantly. But one of the things as a plantophile, I love plants, and so I don't want to kill them instantly, but I want to know how they respond to stresses. So rather than going to a really high concentration, I create what I call a gradient. And that's going to be it's a really fundamental challenge in chemistry. Oops, I'm going to stop. Oops, a daisy, share my screen. It's a really fundamental challenge in chemistry. Let's stop share. And so this is one of the things I really want. Excellent. When you are, so yeah, great, Christine. So this is one of the things that students really need to do to practice. Is how do you make a solution? Okay. So what do we need to know? I'm just riffing here. What do we need to know in order to make up a solution of salt? So everyone's got some salt in their kitchen. I've got that pink Himalayan stuff. And everyone's got some water in their taps. And this is really important. So dissolving ions into solution is something we do every day in the laboratory. It's a really important skill that's used in so many jobs, whether you work in stem cells, whether you work in astrobotany, whether you work in medicine, there's even non-academic places, like dissolving solutions to a correct concentration is a really important skill set. And so, yeah, I'm just waiting. So it's Christine. So dissolving solution. So once you've dissolved your salt, and we're going to go through that shortly, you then want to dissolve. You want to then dilute it. So who's heard of homeopathy? Homeopathy is where you take some a flour and you put it in some water, and then you dissolve that water again and again and again. And essentially, apparently, then you get an essence of the of the plant in the dissolved water. And some people think this is a good medicine. Placebo is a fantastic medicine and a lot of controlled studies. But understanding dissolving things is a really important skill set in science, and this can allow us to find a dilution of salt which plants can grow in. So we don't just use really high concentrations that kill them. And I'm hoping Christine is going to want to come in here and
she should be good to go.
Hi, I'm good to go.
Oh, fantastic. There she is.
Is that a good setup? Sorry, I was having some technical issues there and I had a few windows open and it wasn't letting me unmute myself. I wasn't letting me unmute myself. Apparently, I'm the biggest factor there. Hi, guys. My name is Christine. I'll share my video. My name is Christine. If you don't know who I am a teacher in Southern California. I teach astronomy, honors astronomy and chemistry, and my students are actively involved in collecting authentic data in the space environment using high altitude balloons. We are very excited to come on board with Magnitude this year, and we were in the process of doing our ExoLab experiment when we went remote. I had been very much hoping we were going to utilize the Magnitude platform to launch our high altitude balloons this year. This is going to be now the first year in 8 years I haven't got to launch with my students. So I'm pretty bummed about that. But one of the things that's really exciting for me on the educational and curricular lens of this is how we can use this to cross collaborate and pollinate different regions of education, to where this doesn't need to be something that can just be done with an after school, club or an outreach group. But it's really important for me to find ways that we can percolate these sorts of learning experiences within formal education, because I think that's where we can really hit the most students and have the greatest impact. For me, when I look at an outreach activity or something that's in the informal setting, there you already have buy-in. And I think that you have the greatest reach to reach students who may not otherwise be looking for those extraneous activities, when we can, just really do this like knowledge dump within the classrooms that they're already in. And that's where you get the kids that may not otherwise have been engaged, that are going to be our next future explorers. They just don't know it yet. I think this really allows us to really motivate and inspire. So when I was in our group chat the other day and listening to Dr. Barker speak, that really just got my brain going with how can we use this in a physical science class, which is what my forte is. So I went kind of off and running with that, and I created a lesson, which I would like to share with you guys. And give me a second here. What I'm going to be doing is sharing a link where you can participate as one of my students. And there will be a code that's in there. So this is a way that I'm utilizing to teach distance right now and remotely. And you can just kind of see the crude format of my lesson right now that definitely still needs a little bit of work, but you can see how we're taking this exact concept that Dr. Barker is talking about and applying this to remotely learning science in the home that students can do actively right now with any of the materials that they have at their disposal. So sorry, this is loading, and then I'll pop in the code for you. Okay, so in the chat, there is going to be a link.
The Nearpod.
Lori, hi, it's good to see you. I actually did Space University with Lori, so that was so cool to see. Oh, and I see a question for me. What did the experience with the XLab team do you use? That's been so cool to be able to integrate. And, I would love to tell you that our experiment has been successful, but it hasn't. But that's important because kids have to be afforded the chance to fail. We unfortunately contaminated our seeds the first time, and we had to replant them. And then I got my whole module going at home, and it turned out my seeds, even though we used everything we thought we were doing to decontaminate early on, my seeds molded. So it's been a process of science because things don't always go the way you planned.
We could always send you sterile seeds.
I think that's a good point because, I've gotten some that have grown well. Everybody can hear me okay? I think that hopefully the Wi-Fi is working all right. But some of them are molding, and it'd be interesting to be able to compare which ones we're getting success with in the way we've done it, because some of them have done great, and then others I've got a set from the soybeans, and it is just pure mold in the dish, and I can't figure out why it would have happened to just that set of beans.
Yeah, and I will say one of the coolest things about that though has been that I was allowed like 5 minutes to go into my class, and I already had things. I had like the Petri dishes and the tongs and everything that were in the autoclave in another classroom. So I had this very quick amount of time. I had my own 2 children with me, and we had to like go through the whole process quickly. So I feel like a lot of times as a parent and a science teacher, there's a lot of things I do with my students that my kids don't get to be a part of. So now my own students, my children got to do it, and my module is like sitting over there in our entertainment center. So I'm going to share my screen right now, and I see a couple of you guys are in. You should be able to put in your name. You should now see my screen that says Plants on Mars, a chemistry lesson. And some of you guys are not very good students right now because I only have Ted and Richard that are in.
You get a star.
Come on, guys. This is how I take it. Participation.
Yeah, do I get a star?
You get bonus points. First one in. So once you get in, it'll ask you for your name. This is always fun with students. They are taking it serious now because we have this whole Zoom bombing issue, which happened to me for the first time this week. Adam Sandler wanted in my class. And
Really?
it's actually, yeah. And James Franco. I almost let him in. Thank you, Tony. So for the rest of you guys, you can just get in as you see fit, but there are some participation components of this. So you might want to. It's fun.
Good idea.
It's like this too. So it's just a cool way to facilitate distance learning. So for those of you that are in, I asked you what your role is.
I'm gonna be other. Just because I'm difficult. Oh, I'm a space fan.
You can be space fan.
Space fan.
So one of the things that I really enjoy doing is immersing myself in the science so that I can make that something that is meaningful, attainable, and relevant to my learners. I've had the opportunity to do some pretty awesome things as a participant. I got to fly on NASA's SOFIA mission. I got to represent the US as an astronomy ambassador in Chile this last year. And those experiences are important as an educator because it's how we disseminate that information. So sitting and hearing Dr. Barker speak the other day about these astrobotanical connections, which is not the way my brain works. I don't think about cells, I think about stars and rocks, and I'm a macro scientist. So I like to see this big picture connections. So for someone that's a physical scientist, it's harder for us to grasp the minutia that's involved in things like biology. So I like to look for these overarching themes. And educationally, this is also what NGSS is looking for as well, as these cross-cutting concepts that are percolating through every content area. So you will see some matching things there. And this would be something I would have students do too. In modeling good teaching and idealistic learning, we want to capitalize on students' moment of being open to learning and most receptive. And studies have shown that that is in the first 10 minutes of learning and the last 10 minutes of learning. So I always like to model all of my lessons to capitalize on those points. And this is a platform that I found hugely useful in distance because the kids they're checked out anyway, but now they're extra checked out. So for those of you that are not in, they are all seeing a series of pictures that they have to do a word association with and match to the word. And remember, this is a chemistry lesson. So there are some things like alkali metals and sodium chloride that they're having to match to the lattice structure. I might have given you a hint there. And cool, Ted and Richard, you got 100%. That's awesome.
Oh man, I'm being judged live.
Like the asparagus thing, can I allude to that quickly? So like a lot of these things were discussed earlier, like there's the maps.
Yeah, Carthage.
Carthage stories. So you're like, so the way you design these questions is to help the students reflect on the concepts that were discussed earlier. Like a good joke in a comedian's like lineup. They refer back to earlier jokes to remind you, get that chuckling sensation stronger. And that's how you ensure the lesson goes in better. That's a really great idea. I'm a big fan of that. And asparagus. Can you remember what asparagus has to do with gravity? Can you remember that link? Or so like the asparagus, we were discussing it yesterday because asparagus is probably the only crop on the planet that has its value affected by gravity. Because if you leave asparagus stems on their side, they will bend away from the direction of gravity. So like there's an annual loss of like revenue based on asparagus that's undergone a gravitropic stimuli. And for me, this was really exciting because I've been researching gravitropism for years and never found a way that it actually made sense or use in reality in the real world until I encountered this part of the economy. Like, so things that seem seemingly like non-valuable or non-applicable to Earth, eventually, if you sometimes do become relevant to everyday life, if you know asparagus farmers.
Yeah.
So back to you. Sorry, I just got excited.
That's perfect. That's actually what I'm going to defer to you here in a second as well. So as we were chatting the other day, those are the ways I was going with this in order to make a chemistry lesson. So as an educator, what I would do would be to facilitate a lesson like this in order to encourage students to participate in contributing their ideas towards which legumes would be used next. Because I feel like there's two groups of students. So the students that would see that opportunity initially and just dive in. And then there's the students that are going to need to be inspired. And I feel like for students that don't need to be inspired, they don't need me. And that's not most students. Those students are doing fine with remote learning and they're doing fine with distance learning. But for the rest of the group, they do need a little bit of a push here. And this is where we can make those real world connections to the space industry. And as an astronomy educator, that's what I feel like is the most important role that I fulfill, is for students to see the ways that space as a whole, the industry, the science, how that relates to humanity and providing that human element. Because these kids are going to be the decision makers, the deciders. They're going to be the next explorers. So we're imparting upon them a huge responsibility. So we need to equip them with the skills to really do something with that. So the components of this lesson I was looking at were the fields of Carthage for a hook. Would you mind speaking to that, Dr. Barker? You shared this amazing story the other day. And I tried to find some really good resources on that. I didn't find that great of resources, but this is so interesting. I feel like any student would be interested in that. So would you speak to that?
Yeah. And I'll dig out some resources and send it for sharing.
That'd be great.
This was a story, when I was in Nottingham, the University of Nottingham, there was an old professor there who researched plant nutrition. And his research had got him fascinated by salts. And he'd gone through, because he was a very old dude, so he'd gone through many, many books. And he found some old history books in which they described this event in the past. I briefly alluded to it earlier, but for those of you who have joined us more recently, there was a moment in European history where Rome had expanded its influence across the whole of the Mediterranean area. And there was a rival civilization down in North Africa called Carthage. And there was a moment when one of their leaders, Hannibal, rode his war elephants all the way through Spain to Rome and sacked the capital of the city. And this was a huge tragedy for the civilization at that time, to have its capital destroyed in such a way. And so sure, in the future, after that, generations later, Rome got a massive army together and they went to Carthage and they also sacked and destroyed the city. But they went one further. The historians wrote that they sowed the fields with salt. And that was to ensure that no civilization would rise at that location to challenge the might of Rome ever again. So it was like a kind of a form of chemical warfare, you could say, probably the first documented version of that. And it worked. No city in the Carthage region has ever since formed an empire to challenge the might of Rome. So, so from this historical situation, we have lessons important for us now to ensure that our civilization doesn't undercome the same fate as Carthage. And so that's why it's important to understand salts.
And I feel like there's not a student alive that wouldn't hear that and be instantly engaged. So I feel like including that story is so crucially important, and it completely ties in to the lesson because the students have then been exposed to this historical connection, a chemical connection, and their brains are going to be turning with the question of why the heck did that happen? So my lesson, I included prior chemical knowledge, and this could be easily adaptable depending on the age. Students are introduced to molecular theory in 8th grade and then in generally 8th grade, regardless of the state, regardless of the adoption process of NGSS. So they would be introduced to basic Bohr models. So I included electron configuration, ionic bonding, and alkali metals. Alkali metals would be a trend that they would also be introduced to in 8th grade. The process of ionic bonding as opposed to covalent bonding, the transfer instead of the sharing, and electron configuration would be more high school. So easily adaptable either way. So this was the experiment that I wrote out. So having the students determine the concentration of kitchen salt to grow seeds found in their home. And Dr. Barger had mentioned even using things like coriander, so like something in the spice cabinet. And then the goal would be having students experiment with various concentrations. And we talked about using vermiculite to be able to grow plants and set an experiment that the students would determine based on their targeted molarity. Again, depending on the age, they could calculate the parts per million concentration. That's one of the NGSS standards. It's relatively simple math. They collect their data, they graph and analyze, making a compare contrast. They look at the trends. These are all high order thinking skills, and it would involve, no cost, just things they could do in their kitchen to actively do science with meaningful implications. I then always like to include an argumentation from evidence. And this is one of the science and engineering practices of NGSS. And again, really incorporating those high order thinking skills, because just having students collect data doesn't necessarily translate to a connective meaning. So it's important to make sure that they can connect what they did with what the heck it means. And this is where we can get in those literary elements. So, here is what the beginning of my lesson looked like. How can we use chemistry to select plants that are resistant to salt? Obviously, that would be something that could be changed. But I put in these two guiding questions. How can we decide on the best concentration of salt to successfully grow plants? Which plants are resistant to salt and soil? So I based this off of the 5E model. So I used an engage and then a concept check, relating this back to valence electrons and relating that to the process of ionic bonding. So they should remember that we're talking about transfer of electrons, not sharing of electrons. So I give like the hand holding model, one of the two. They have the Bohr model here. They have to connect the atom electron configuration and then the ion electron configuration. And then I made a writing assignment. One thing that we use a lot of times in science is a model called the claims evidence reasoning model, where they are given a concept or a guiding question. The students have to make a claim and they have to separate out their answer into evidence of what they can see and the reasoning to explain what they know. And being able to differentiate parts of their answer and then making a conclusion. Because what I always tell students is that an opinion is just an opinion unless you can back it up. So this forces students to critically think about what they did, what the meaning from that is, and how they're going to communicate that in a meaningful and academic way. So that's the lesson that I made up. Are there any questions?
This is fantastic. I'm just glad you didn't challenge us to actually fill some of this stuff out.
I thought about it.
The last two slides were really nice. So if we could actually think about how we can break these concentrations down, would you, either you or Dr. Barker, walk us through what that might look like in a couple minutes? And so let's say I wanted to run up to my kitchen at the end of this session and dilute something. How would you go about doing that then to understand the molarity of my new solution? Right? And say I want to go from 100% or 50% down to 2%.
So there's two concepts that we're going to need here. We're going to want to have like a goal, a target, like a concentration which is scientifically insightful. And we're also going to need to have a starting point. And that starting point is going to be the actual molarity of salt. So sodium chloride, NaCl, what is that? And I don't know the answers here. This is the other thing. Like often I have students come to me, I'll be sitting there programming something on my computer and they'll have this like chemical challenge. And I'll go like, well, I don't know all the answers off the top of my head, but we're at a very lucky time. We have Google, like have all the answers to all questions of humanity are basically there. But what we do need to know what is the right question to ask. So it's not about having all the answers. It's just about having, the perseverance to find the answer, and then someone to help you find a way to restructure your question to get to the answer. So we're going to need to know the molarity of salt, aren't we? Why is that? Because we're going to want to know the concentration that we go to. So I'm going to go look in the literature for a target concentration. And hopefully one of the other participants here, because I like to work as a team in my research laboratory. A lot of people think you have to find the answer all by yourself. That's only in the exam. So don't worry about the school just trying to make you pass the exam. We're trying to make you work as an awesome member of an awesome laboratory. So you can be a team.
And one thing I always tell my students is whether they're flipping burgers or building spacecraft, they're always going to have to work together.
Mm-hmm. Yeah. Right.
So flipping burgers in space. Well, 'cause
Stem
what
cell
happened-
burgers.
That's my question.
That'd be like catching burgers in space.
Right.
So I'm now like, I had a paper open earlier with the answer on, but to make it a fair test, I then also closed that paper down. So
was it 58 grams per mole? Is that right? No.
There are several online calculators that you can use that look at the amount of salt by gram or ounces, and then mixing it with water. It's getting a little bit off of the molarity part of it, but they're depending on their level of that they're at, they may not engage in that higher skill set knowledge. But generally, there's some charts out there that give the percentage of what seawater would be like, hypertonic, isotonic, basic drinking water, but they can figure out how much salt and how much water to mix based on some of these online calculators. You know, it's really easy to come up for them to look at it. And even, you know, they may not have a kitchen scale. And then as teachers, we can kind of equate it to what would be a teaspoon, right? Because they're likely to have that type of measurement tool in their kitchen.
Yeah, and then, you know, if they know that like a gram and a milliliter are equivalent, you know, they could do you know, an analogous determination.
So the first thing that I like to do is try and work out how to make a 1 molar solution. And the first time I do it, I always do it to 1 liter. It makes the math much more simple. And those online calculators will allow you to change like the amount of the solution that you're going to make. So you can say, maybe I only want to make 10 mils of this solution. But mentally speaking, if you want them to do the math themselves, I always try and work out 1 molar per 1 liter first, because then you just need to know the molarity of sodium chloride, and then you have to mix that number of grams into that 1 liter, and then you have a 1 molar solution. And then you can just dilute it down from that 1 molar solution to become biologically meaningful concentrations or environmentally meaningful concentrations. An environmentally meaningful concentration is salt water, just like you alluded to earlier. For me, I'm interested in the biologically meaningful concentrations. And for that, what I did was a quick Google search, and I wanted to show you how I came to the answer, because it's quite easy. I typed in Arabidopsis, and I alluded to my little hero earlier, Thaliana. I added the word salt. Essentially, I started searching through the literature for a study, and there's a bunch of them here, and each of these will have different experiments that they performed. I'm just going to go back to my history to one I opened a second ago, because we're going to be after one. Oh, I shouldn't close the slide, should I? Genetic response. So you just go through the papers, and then some of them would have done a concentration gradient. So I'm just scanning down through, I'm looking for concentrations of salt, SOS. So this is the right genetic pathways. So this is the salt oversensitive response pathway. So this is how the plants respond, but we're not trying to get into the genetics. I'm just after a concentration target. And unfortunately, that one didn't. So the first one in the list didn't work. But that's okay, right? Like, this is the nature of real research. Like, you're not always going to get the answer first time. One of these experimental papers is going to have a salt concentration that is appropriate. Ooh, look at this. Let's have a look at this figure. I'm going to pop that open. And honestly, I'm doing this live. I've got no idea what we're going to find here. But yeah, here we go. So this low-grade figure, it has salt concentration, NaCl, that's the one we were looking at earlier. There are other salts, potassium chloride, lithium chloride. This one here is called mannitol. So mannitol is not a salt, it's a hydrocarbon, it's like a sugar variant, and it provides an osmotic stress. So there's 2 types of stress associated with having salt in your environment. You have like the sodium and the chloride with their like free electrons, like trying to interact with like proteins and stuff and cause them to denature. But you also have an alteration in your osmotic potential. So you have a change in the way that water moves around.
And so this is what the mannitol control is here for. So this is a legit research experiment. This is a next level up. So I wouldn't worry about that one for now. But essentially here we can look at sodium chloride. So this has both the osmotic stress and the ionic stress that's caused by salts. And then along the bottom here, we have these concentrations, 50 millimolar, 100 millimolar, 150 millimolar. And so as we go up in these concentrations, we can see the size of the plant reducing. So the more stressed you are, the smaller you are. The happier you are, if you've got a nice environment, you grow big and you get normal. So what we have now is a target concentration. So I would want to grow the plants at say 50 millimolar and say 150 millimolar. 150 is probably likely to kill the seeds and stop them from germinating. Maybe there's a bit of variation there. And then here at 50, we'd probably get some that survive and some that are susceptible. So you can see here, the moral of the story is all the answers are there. We've just got to get them to ask the right question. And all I did was Google a couple of words, and that search was just Arabidopsis thaliana and salt. And I only went down like the top 2 studies that came up in Google. It wasn't that long. And so I think to ask your students to just search in the literature for a little bit is a plausible way to spend a short period of time. So based on that, I've now come up with a goal, right? And the goal is to work out how to generate a salt solution, which is 50, 100, and 150 millimoles. So we have these online calculators. I think some of you might have found them. And again, I would always do on a pen and paper because I'm old fashioned, and I'd be like writing out 1 liter. I'd be writing out the molarity of sodium chloride. We're working out how many grams I need to put of sodium chloride into 1 liter to make a 1 molar solution. And then I'd be working out how to dilute that down. But maybe one of your online apps has got a quicker solution. And I'm going to stop sharing and hoping that someone might have found the solution. But and essentially the thing we've just discussed there is some of the questions that are on every GCSE and A-level exam. So that's the English equivalent of your high school diploma kind of thing. So the questions that I asked are in like the high school exams, and the questions that I asked are ones that I have in my laboratory every week. So when you get to, and not just my research laboratory at the university, but like industrial laboratories that my friend Kai and other people work at around the world, these are the types of calculations they do. And so this initial lesson plan that was so beautifully demonstrated by Christine is challenging the students to acquire the skills that they need to go into the modern workplace. So I think that's awesome, which is nice.
I'm on mute. There we go. So using these calculations, we can basically suggest if we're going to look at our legumes, what threshold will they be able to handle this this salt? And we've run them all through the same solution, so they're all equivalent. And it really comes down to the care and measurement, right? I mean, you can just grab a scoop and say that's a teaspoon, right? But is it really a teaspoon, right? Or a gram or what have you. So that measuring has everything to do with if you're dealing with something so small of a concentration. And how do we ensure that what we're using in the kitchen is going to be as accurate, or what 5% difference, 2% difference? At what point does it become like, really, it's not an accurate measurement? You can't eyeball it, right? That looks like about half, right? It's like
well, in the lab at work, we would use a digital scale. It only needs to be to 0.1 gram accuracy. So you can do 1.1 kind of thing. And I don't know what the average digital scale is at home. I know not all homes have digital weighing scales in the kitchens, but some do. But I do know you can get them on Amazon for like 10 or 20 bucks, depending on like the brand. So digital weighing scales are not expensive. And if you do have access to digital weighing scales, you'll realize the amount of salt that you need is actually really quite small. But yeah, that's part of the challenge, isn't it? citizen science.
There you go.
So
You might
here's
even be able to build your own scale. As we learned today when we launched that high altitude balloon, we use a nickel to represent 5 grams and a penny to represent 2.5. So you can start doing some estimating if you want to play around with that. In fact, where is our balloon doing anyway? Liam, do you have an update or should I take a peek? We launched that a little after 8 o'clock this morning. And right now it's, it's actually gone down in altitude, or is it? Yeah, oh my goodness. It's taken quite a knock. It went from 20,000 feet down to about 8,000.
Oh, cool.
Yeah, so it's actually heading down. That's not good. I wonder if it got caught in some rain. I'm gonna guess that's exactly what happened. But our model did show that it was struggling to get out of California. Let me just show you. This is what our little hab looks like right now. How's that for a segue, huh? Measurement to where's our balloon? And so it's dropped quite a bit here. The last reading I have was at 14,000 feet. It was climbing. It was up to 22,000, and then it got hit by rain, I'm going to guess. And that rain's taken it down 20,000.
See, this is actually really interesting. So whenever we do experiments, we have a hypothesis. So if we refer to this balloon flight as an experiment, which I think it is, then the hypothesis was that it would fly up to a certain altitude, right? When we look at the data associated with the balloon flight, we see that it didn't fulfill our hypothesis. So this happens all the time when we do scientific experiments. This is when we start to look in what we call metadata for alternative environmental characteristics that could explain what we see in the primary data. So this primary data is the height of the balloon. And so this is actually one of the wonderful things about being a scientist, because you're kind of a detective. Every time you do an experiment, you have the hypothesis, you may see it happen. Keep it up, grit is the only way. A lot of them go wrong. A lot of them have other factors that come into play and change that primary data. And you need to then go through and play detective to try and work out what are those other factors. Is there ways that you could have monitored them, measured them? And can you then take quantification of them in to explain what you're seeing? So I'm thinking now there's probably a weather satellite somewhere that has a web link, and maybe a way, and it could take a long time to do, but you'll be able to go into that weather satellite database, pull out that information, go, yeah, look, there it is. It was raining at that time. There's a cloud in that area. And
that's exactly what I'm doing while you're talking. But let's do this. As I realize we're a little after the top of the hour, I want to refresh everyone with what the Leguminaut challenge actually is and how this is important for all the things we've been talking about already. We're trying to determine this next plant that we want to send in this symbiotic relationship with the bacteria. And we're really kind of open-ended. It has to be a legume. And we have some candidates. A lot of our teachers that are here in the Zoom have kind of selected and are supporting a particular legume, but it's up to us, you as students and other teachers that are joining us, to give us an argument, a reason why, and that can be a creative artistic reason. It might be a recipe, it might be a piece of art, it might be poetry, something you put on TikTok. But I also hope that as our students are a little older, are thinking about scientific benefits and reasons of why we want to do that. I think that's pretty important. And Michael Wilkinson, if you're back on, I know you're jumping back and forth between your classes today.
I'm here.
Fantastic. I'm wondering if you can give us a nice overview, and this you can lead right into your class. I think your students will be joining us at a half past the hour. Is that right?
Correct.
Wonderful. And so that's going to be interesting. And I'm going to open this up to all the teachers that are listening and those that have been active in our group. We've got 5 remaining, is that right? No, well, a number of sessions, 5 or so remaining sessions here after this one today. If you would like you and your classroom to join us for a conversation, reach out to us, hello@Magnitude.io. And we've started to see that Lori did that with her students. And Michael's about to do that with his. We don't have a lot of slots, but I think it would be fun if your students are looking for some engaging ways and way to kind of stoke their interest about what we're doing here. Bring them on, have a conversation. In the case of Michael's students, privacy is an issue for our younger kids. And so they're going to be watching YouTube Live and then asking questions of Michael through his Google Classroom account. And so he's going to be watching multiple screens here, I guess, as he's working with them. But why don't you, if you can, Michael, share with us what the Leguminaut challenge is. And when your kids pop in, well, then we'll move over to that.
Okay, cool. So this is, there you, then they always tell you in press things, don't start out the sentence with so. Try not to do that. It's like, it's ridiculous. The Leguminaut challenge, I think, is just, it's ridiculously exciting. If you were here earlier in the broadcast, you heard Gil commenting on how our students, and we had some students on here, they've got the chance through this challenge to actually literally change the world, change the course of humanity. Legumes are a major food source. They've been with us for millennia, and they're, you know, high in nutrition, high variability in terms of flavor, and what we can do with them in terms of how we prepare them. They're great forage crops, so it helps agriculture move along, and they're going to be a really important crop for us to use in space. If we're going to spend longer than a year and be further away than the International Space Station, where we can get resupplied every couple of months, someplace further out like the moon or Mars or an asteroid, the astronauts are going to have to be a whole lot more self-sufficient, and that's going to require a reliable food source. We've talked about the nutritional issues that, you know, the nutrient content of even the packaged food, it breaks down after a few months to a year. So it has a limited shelf life, even though it's not going to spoil per se. You're just getting roughage. You're not going to be able to get any nutrients out of it. So you have to have some source of fresh food. With thinking about horticulture growing, you have to provide the nutrients through the soil, roots dissolved in water, so that the plants can grow and be healthy and produce the fruit or the vegetation that you're after. That requires nitrogen. That's our major limiting factor, and all of us are nitrogen based. We talk about carbon based, but really, if you think about the proteins, we're nitrogen based. You cannot build DNA without nitrogen compounds. And through this incredible symbiotic relationship between legumes and their symbiote rhizobium, a soil bacteria, they are able to take the nitrogen from our atmosphere, which is inert. We're swimming in it literally, and it doesn't do anything. Those two nitrogen molecules are bonded together, and it takes a tremendous amount of energy to break them apart. So
there's that chemistry connection again.
That's right, and the physics, right? It's PChem. So that amount of energy, it requires tremendous amount of fossil fuels. You literally have explosive compounds that you're working with. They're heavy. You end up producing ammonia, which is deadly in an enclosed habitat, especially in microgravity. So there are traditional fertilizer methods that we've used for mass agriculture are not going to be sustainable, and they're already not sustainable on this planet. So we need a biological solution. And you've heard Richard talking about this, that there's some changes, some significant changes in how organisms function in microgravity. I just came across a new article that's talking about how the epithelial cells that line our gut, our intestines, are affected by microgravity and may have an impact on how we're able to tolerate contaminated food, different pathogens. We may be more susceptible to food poisoning in microgravity. So just all of these changes that the microgravity environment creates. Can the rhizobium nodulate with the legumes on orbit? If they can, we've got a viable solution for turning that regolith into viable soil. We've got a chance to grow crops sustainably and not be just eating beans. We can grow grains and fruits, you know, tomatoes, peppers, things that are really nitrogen intensive, have good nutrient value to them, but they would never be sustainable crops in space otherwise. So that's kind of the science behind this. This is authentic research. Nobody knows the answers to these questions. Nobody. But I'm sure your students are going to be able to help us, if not answer the question, get one step further down that path. And we've got to try these experiments over and over to make sure we have an understanding of what's happening. Richard was showing some of the databases that connect us to the genetics. The older students can dive into that and see where the legumes and where the rhizobium might be good matches. So there's this wide range of applicability. You could have the youngest of your students simply observing the legumes and seeing how they grow, trying out different kinds of potting media, trying out different legumes, cooking them and seeing which ones they like the taste of best, to the older students actually doing more of the physiological, the chemical, and the molecular analysis of these candidates. So we're going to be working in basically 5 phases. We're currently in phase 1. We're really just exploring legumes, and we've got some content on the platform that we're offering free to give teachers some guidance around that. We'll be posting our ballot later, probably a month from now, early to mid-May, and you and your students will want to cast your vote to nominate the Leguminaut candidate by May 25th. And that's when, about June 1st is when phase 1 draws to a close. Will the free content will still be there. If you have a summer program and you want to reuse it, you can rerun these broadcasts to support your teaching faculty and your students. We will be around to support you if you have questions. Phase 2 starts with the new academic year for North America. I'm sorry, phase 2 is in summer, and that's by invitation. We're going to be testing out the flight protocols, the media that we're going to use, the conditions at which we're going to grow them, what kinds of containers we use on orbit, our planting, how old the plants need to be, because we're really after not getting to the point of nodulation. So we need our plants to be a little bit older than just seeds. If we send seeds or even germinated seedlings like we did with Flight 7, we're not going to be far enough along in a month to reliably have nodulation. So we want to make sure that that's a little bit further along, and those all have impacts into how the experiments protocols are designed. In September, then you can come back with your classroom and join the ExoLab platform. You can secure your classroom lab or your resupply if you already have an ExoLab, and we'll start with pre-flight testing, and you'll grow the selected legumes using the chosen media in your classroom, go through observations, get the beginnings of those ground trials, and that will run in 2 phases. The first being in autumn, and then the second in the winter. So it'll run into just before the launch, which is phase 4. Launch is scheduled for February of 2021, and you'll actually be able to fly along with us through your ExoLab and see how the plants respond to the microgravity conditions, how they function on orbit, and make those comparisons side by side to the plants that you put into your ExoLab. So what's the difference between 3 and 4? In 3, you won't actually have to use your ExoLab to run the trials, although you can, and then you would be comparing to other ground stations that we have set up. And then
make a note there if I can, Michael.
Yeah.
So what we wanted to do, I think the planet is under this extraordinary circumstance right now with the pandemic. Schools have shut down, many for the rest of the normal school year. And so we opened our platform up at no cost.
We just lost Ted. So we opened up our platform at no cost so that we could really support our community of educators and learners. It's a great opportunity. We're learning from each other. We have these broadcasts and really developing best practice during this challenging distance learning environment. And who knows? I mean, we don't really know where we're going to be in September of 20, to be perfectly honest. I'm in New York, and we just definitively are not returning before May 15 and may not return the rest of this school year. And some states have already made that decision that they're not going to return. Most universities and colleges are not returning this academic year. And there's even some question in terms of how summer programs and fall semesters will be handled. So we're really developing a community of educators and learners here, and being able to support each other in these difficult times. And then you'll have something that is ground tested and teacher and student approved and ready to go with your next semester. Hey, welcome back, Ted.
Yeah,
I tried to anticipate what you were going to say, so
I'm sure you did fine.
Okay.
We'd love to have you all, basically, is what I'm trying to say, and we can work it out with you. We're going to have some pre-orders set up for the fall. So if you need to do some budgeting or what have you, just reach out to hello@Magnitude.io. We can get you squared away. But you can go quite a long ways with us here on the ground prior to launch. Sorry about the bad connection. Go right ahead, Michael.
Absolutely. So, and then we're even looking at our phase 5 then would be after the specimens return from space, to be able to do some post-flight analysis, both just what they appear, maybe do some microscopy, but definitely we hope to do some post-flight genetics work and see if the nodules, if and how they were affected by that microgravity environment. Also, we have hypergravity environment. We have positive Gs on launch and reentry. The payloads and the astronauts experience more than 1 G. So that really, in and of itself, can cause changes. I don't know from our PIs if there are other points they want to throw in there, the other teachers that are with us, questions you have about that process and how you can be a part of it. If anybody from YouTube has questions about that piece of it.
I think you covered mostly everything there, Michael. Maybe just a word out to those elementary teachers who are similar to myself in my background, although I've had a few of the high schools along the way, but not to be fearful of getting involved in this. We've got some really high level scientists talking to us and all of that. And at some points, it can really seem like it's a bit heady, but you can bring it down to the level of the elementary kids and get them involved. The palette is wide. It's really, really wide. And I think it would be super, super exciting for really young children to get in on the ground level of this and start the process. Ted said earlier, creating little recipe cards. I would even throw in drawing posters and stuff like that. Keeping drawings of beans that are growing in their classrooms. And if you're listening in from Canada, we want you on Glycine Max's team. So certainly think about that. Don't hesitate. You don't have to be a biologist. You just need to be what you already are. And that's a teacher, and that's all you need to be.
And I'll add as well that this is an ideal time to do project-based learning. And kids are tired of the typical, let's see, I'll move. I might be losing sound here again. Let's see if you can hear me better. Hopefully that's a little better for you. Kids are tired of the worksheets, the printables. They're tired of the
Oh, Lori.
I sent her a message to her phone the last time, and she's not realizing it.
Oh, you can't hear me yet. Okay, well, I'll try and come back in.
Oh, I think you're good now.
Now, is that working now?
Yeah.
So I guess my point, the overall point was project-based learning is an ideal way to go for the rest of this semester, rather than trying to assign worksheet after worksheet in a distance forum, because the kids are tired of it. We know that even at this point of the year in a classroom, they're tired of it. So.
That's a great point. Let's find ways to have fun and be engaged. Students, if you're out there, clearly you're looking for something to do if you're watching our channel. We got some really exciting stuff talk to your parents if you need to, or your teacher. Come aboard, help us find the next plant to send to space. Let's have some fun. So one thing we can do as while we're waiting for your students, Michael, is if any of our teachers here want to talk a little bit more about their particular legume outside of a pitch, you know, so what's so special? Maybe you want to talk about your amino acids or the proteins or the carbohydrate ratio or special vitamins that your particular legume might have as a benefit. It's good to know too.
I think Renee is ready.
Yeah, Renee, what you got? Alfalfa.
Alfalfa, go alfalfa.
They're all alfalfa.
The dogs are chiming in. So again, you know, one thing that I'm working with is some homeschool families, and they're excited to be getting the seeds. Of course, I'm hoping that they will pick some of my leftover seeds for Team Alfalfa, especially when we think about all the pieces of the puzzle between being able to have them in the rocket, the cargo space, you can pack a lot, that you can get food quickly. They give us all that we need. Again, go Team Alfalfa. But really they're devising their own kind of experiments, and I'm excited to see what they'll do. You know, as we think about one thing that we talked about today, one thing that people don't realize is the salt content on Mars. And, you know, we think about some of the other pieces. Right now, we're working to create a regular lesson. So I'll be excited to be tying in some of the Astro Botany pieces and information today into that lesson. So again, as I'm just going to echo what was said, this is a great opportunity to have something that you can do with your students. You know, even if they may not have these seeds at home, just talking about germination, and maybe they'll learn something in drawing and thinking of all those things and say, hey, I have, you know, a lot of times another bean in their home that they may be inspired to start their own like science journal, their own experiment. And that's what I think is great about this. But of course, pick alfalfa. That's pretty much a quick summary for me here in Providence, Rhode Island.
Yeah, thank you. Well, what I forgot to ask Fatima was, I saw her plants growing in her Martian regolith. I wanted to know what her formulation was, because she wasn't getting some of the challenges and problems I was having. And they were going. It looks like they were doing pretty well.
I'll definitely check in with her then.
Yeah, so can you share a little bit about that? What was
I'll have to check in with her, yeah, because I don't know the exact details of how it was going. So that's why I brought you into this call, to actually explain, but I'll check in with her.
Oh, that'd be fantastic. Cool.
Sure.
Yeah. And I guess our other students probably have left now. It's late for them, but Shivar is from South Africa, which is great. And who else do we still have from around the world? Canada, right? Japan's gone to sleep.
Okay, this is interesting. Now I have a real empathy for the news broadcasters. I've got fifth graders yelling in my right ear, and I'm trying to pay attention to all y'all in my left ear, and I've got 3 screens here simultaneously. So
let's do this. We'll let you run the show.
See how this works.
Yeah.
So I've got a crazy group of fifth graders who are, like all your students, are trying to manage the terrain of isolation. And, you know, one of the things that's difficult for them is not being with each other every day. And that physical presence, and they're kind of all kinds of creative ways to stay in touch socially. They've been doing their own Google Meets. They've been playing games with each other online. Just hanging out together. So that social piece is just so important. And these broadcasts every Friday have been incredible for me for the same reason. I get to meet up with some amazing colleagues and associates and friends every Friday. So it's a nice way to bring the week to a close. I'm just now juggling my classes and interspersing between this platform. So my students are going to be starting the trials. I sent them out a sample, and we'll be just how we're going to plant them, and they'll post their ballots later in May that I talked about in the previous segment. They've got a whole bunch of questions related to the whole range of things that we've been doing, from the micro or picohab to life on the space station, to the plants themselves. And the questions, if you were in earlier, Gil talked about how incredible the questions can be and how they can really lead to significant and powerful research. Some of the questions our panel here is going to be able to answer. Some of them, the best answer is going to be, I think you can figure that out through the experiments. And some of them are going to be, gee, I don't know, but I think maybe there's an expert we can tap, or wow, we need to create a new experiment to figure that one out. That's a great next step. So I really encourage everybody to chime in here as we go along. This is this is a new way of approaching this, and give this a try. In terms of my students, I hope you all can hear us. I don't know if you can. Yeah, some of you I see are showing up in the YouTube, so you can post questions in that YouTube chat if you have that availability. And Tony, you'll just let me know.
Yeah, we'll monitor YouTube for you if you want to look at your classroom channel.
Yeah, I'm looking on the classroom channel, so that's going to be the best.
Okay.
So I've got Aslan. I'll take his question first because he's doing an incredible job of moderating and redirecting my students as they check in to our class hangout, sending them to the YouTube link. And so I'm just going to, as a thank you to the hard work he's doing there right now as a manager, I'm going to start with his question. And Aslan asked a couple of things. One is, when will we start solely relying on space-grown food?
Wow. I guess we'd have to think about.
Yeah, I kick it off with an easy one.
Sure. Food is produced for something to consume, right? And food's a lot of different. The concern it's humans, and so then we have to think about economics. If you get your bananas, are they being grown in Brooklyn, or are they being grown in Panama? How long does it take to get from Panama to Brooklyn, and how do you keep them fresh? Or your apples or your pears or your strawberries or whatever. If you're growing something, let's say on the moon, how long will it be to get back to Earth? And why would you want to grow them on the moon? Is there something special? Maybe that cantaloupe has a certain flavor that's really rare and special, and if you find a way to bring it back home, it's really worth a lot. I do know Tony's got a friend that actually sends fresh produce from the Central Valley of California anywhere in the world, like overnight. And there's a Saudi prince that'll pay a premium to have fresh strawberries in the morning from California, picked the day before. And so I would imagine some super wealthy person like Jeff Bezos may want that Martian cantaloupe. But that's going to be pretty expensive considering it's going to take 6 or 9 months to get there and come back again. So, but the other thing is, when can we eat food? Well, maybe it's when we're actually living there. And that's probably a more reasonable question. And we're experimenting with that right now. And so if we go and look at our astronauts on the space station, they are growing microgreens in the veggie. And so they are figuring out what they need to do. You are right now, Aslan, and your classmates and everyone else that's listening that wants to do it. We are starting down that path of discovering what those foods might be and how we might grow them. So whether it's that rare Martian cantaloupe that I just made up, or something more practical like a green that you're going to add to your salad because you're now floating above the Earth, is something that's going to probably be more dependent on when the people are there. And how much we're going to really be willing to have dinner squeezed out of a tube. Okay, so
you bring up a couple of points, Ted, that one, this idea of terroir, the characteristics that our produce gets from the soil that it's grown in and the climate that it's grown in. It's a huge deal in the wine industry.
Oh, yeah.
And you mentioned cantaloupe, which is, so I grew up in Iowa, as my students know. There's actually a kind of cantaloupe called a muskmelon, and it only comes from Muscatine, Iowa. And it's the specific terroir that has created this particular variety of extraordinary cantaloupe. So if you can find them, go for it. The other thing is that there is a certain hotel chain that's known for fresh baked cookies upon check-in, and it's my understanding that they have plans to bake those said cookies on their I think it's either a lunar resort or an orbital resort that they're hoping to be able to pursue.
It's not an ad for DoubleTree. I always wanted to go to DoubleTree because I could get a fresh cookie.
But now you can go to DoubleTree in space and get a space baked cookie.
Will it be called DoubleTree or something else?
Yeah, I don't know.
Double legume, right?
The legume-based cookies. There we go. So you mentioned the microgreens, and that's another question that Aslan and Christian and Bryce, looks like almost every one of the kids asked a variation of this question: is what other kinds of plants are we looking at as candidates? This class, actually, some of them worked with us last year on or 2 years ago on the microgreens flight, which was flight 5, I believe. We did a rinse and repeat of it, so they didn't do it live, but they did do it as a replay in the fall. And we grew some amaranth and wasabi and pak choy and purslane, and actually made space salad that we shared. I don't know if you guys remember that. If anybody has a comment, you can unmute your mic and talk in my right ear about the results from the space salad if you'd like to share that.
And teachers there that are here in the Zoom, what would you like to see in space besides the legumes? So the students are asking, what do we grow up there? You guys have any thoughts or ideas? Do you have a preference besides space cookies? I guess you don't really grow cookies, do you?
Well, if I can chime in, they've experimented with growing different lettuce varieties, but salad gets boring after a while. So, and it doesn't contain as many calories as other foods, but you have to balance how many people you're trying to provide food for, as well as how long it takes to grow. And for instance, these tomato plants I've been growing since the beginning of January hasn't produced a single tomato yet. So how long are you willing to wait for some of the food that you're trying to grow? But that's why there's an advantage to the microgreens and to the lettuce, because it's entirely edible, and then you don't end up with as much plant waste. But there is an effort to try and grow chili peppers. Currently, Kennedy Space Center is working on a project to fly peppers to space, and they want them hot and spicy. Because the astronauts don't, that fluid shift in their body, it affects their sense of smell and taste. And so that spicier food is very appealing to the astronauts on the ISS. And so if they can add some chili pepper to it, bring some flavor, that's very appealing to them. So maybe some salsa, throw in some tortillas.
Well, we definitely found in our space salad that the kids really liked the wasabi. It was nice and spicy, and it just added a little bit of zip to your salad. So that they found that as well. So, and that was one of the conclusions they came to was, I bet wasabi would be a good candidate for a microgreen because of that very thing you're talking about, Lori. So, and this also kind of segues off of the points you're making. What parts can you eat on a legume, Jack asks. Well, Jack, it kind of depends on the legume. If we fly clover, go Team Clover. You can eat the sprouts, the seedlings. Got my clover here, and it's got a nice little snappy flavor to it, a lot of nutrients, but the clover doesn't produce any fruit that we can eat. But the great advantage of this is, Lori was talking about plant waste. Look how small these plants are, but they're still packed with nutrients. All right, and they're going to be doing their leguminaut job, we hope, and fixing the nitrogen, capturing it in those plants. We've got our active rhizobium. Not only can we eat this, we can use this to make regolith into soil. I think this one's the key, because glycine max tain't gonna grow before we get
that went from a soft pitch to a hard criticism there. Round one.
And we can send, listen to this, we can send 2,500 seeds per gram. And my students know that's the size of the unit cube or a couple of paper clips. That's the mass. 2,500 seeds. Glycine max can, I think it's 3.
That's debatable. So I'm thinking, just on that note, given that it has already been grown on the International Space Station, now my curiosity, yay, look at that. Look at those beauties.
Head to head, yep. Yeah, see how much further along Team Clover is? Glycine max is just kind of puttering around with some radicals.
Well, look.
Oh, okay, there's the first leaf. Oh, isn't that cute?
Don't forget the tortoise and the hare now. Don't forget that.
Oh, look at those luscious greens. They're ready to eat.
They're beautiful, Ted. They're beautiful.
Okay, gotta get that.
My mind has kind of wandered.
There you go. That's mung bean. Just so gonna little shout out. Mary's not here. I'm gonna.
Oh, look at those.
Mung bean.
And these are all the same age, right?
Yeah, they're all the same period of time.
Yeah.
All in the same medium, all same light exposure.
Oh, they're fantastic.
Yeah. So.
I've been thinking a lot about all the different beans. And one of the things that I have a question, and maybe this is great for the students to investigate, is the amount of water that's yielded in those plants. Because it's going to be one thing to feed us. It's another thing to keep water sources going. Well, I know a particular bean that holds a lot of water. So if we can get the kids investigating that a little bit, what about the water in the plants? How much does it hold? Is it going to be something that feeds us, but also has another role in keeping us hydrated, that also has another role that can do multiple of things, which we know already glycine has been tested for, created for. I mean, we've got crayons made out of glycine max. And what else can they use it for on the International Space Station? But that goes for all the plants, because I'm in for all the plants too. But at the same time, what else can the plants do? What's the versatility factor?
Yeah, we've got that whole bioreactor idea that could these plants be used to help supplement the environmental quality in the space station, the air quality. My students know well that the carbon dioxide levels are rather high on the space station. Could these plants help us to help supplement the scrubbers, the Cedra system, carbon dioxide removal equipment that is notorious? It almost breaks down as often as the space body does. So that might be a way to help us both here on Earth as a carbon sink, pull some of that carbon dioxide out of the atmosphere, and as well as purifying our air in a closed habitat. Annabelle's got a really good question here. For growing plants on the ISS, how much space is available? How much of the needed materials are there? Fertilizer, water, soil, etc. How big would the temperature difference be for the ISS and Mars? So it's a complex question here.
It is, and that's a great one.
And then would the legumes that we send, are they going to grow differently on Mars than they do on Earth, or different on the ISS than they do on Mars or Earth? So she's really looking at, that whole, thinking of it as a whole system. And so if anybody have thoughts on that?
Well, I guess I'll point out that our Exolab 8, when we select that right legume to go with the rhizobia and grow something on the space station, we are going to be constrained in a laboratory box that's 20 centimeters long by 10 by 10. So about 2 of these side by side, or the Exolab that you saw in your classroom before you took the extended break. And so that's what we have to work with. Having said that, that has certain constraints with temperature and air circulation, carbon dioxide. It's a station where you can grow plants. One is the veggie, which you've learned about. It's a much larger area and it's open to the cabin. And so its temperature is a little lower than what our lab is. And there's also something called the Advanced Plant Habitat, APH, which is a environmentally controlled environment with 120 something sensors where they can manage the temperature and the pressure and do a bunch of different things. I don't think they've changed the gravity, but they even able to adjust the gravity in that as well. And then your extended question about on Mars or something else. And terroir, I guess what you were talking about, Michael, in a way talks about that, that these different environments, it's going to change. If I give you a plant to grow in New York there versus growing it in California or South Africa or Japan, that same seed may be growing under different lighting conditions, different time of year, different temperatures, and they're going to probably come out a little differently, even if they all came from the same stock. And so if you think about people growing up, you know, that nature versus nurture thing, if you are in an environment which you get all the nutrients and what have you, you're probably going to grow up nice and healthy and strong. But if you're a part of the world where you don't have all those things, then maybe your body doesn't grow the same. And so there's also some things to consider. If you're investigating this at a deeper level, ask yourself, are there any deficits or things that might take away from the success of the plant that you want to grow? And then will you need to supplement it? Or will it have an abundance of something and now, you know, it's even doing better than what it did before?
And that's actually a great place to go with experimentation, Ted, is stress your plants out. What stresses can they tolerate? Are some more tolerant than those? The earlier episode or segment today was talking about salt stress. That's a reality here on Earth, and it's definitely going to be something we have to deal with on Mars. The soil is very salty. There's something called perchlorates there that are toxic to living organisms. So we're going to have to figure out a way to clean those out of the regolith if we're going to convert that to soil. And we're going to want the plants that are most able to tolerate those stresses. And one of those stresses that Elise raises is, so Mars is so cold. How are we possibly going to grow plants on Mars? I can answer that. I mean, at least I don't think we're not going to be able to grow plants outdoors in Mars. We're going to have to create a habitat, like think of greenhouses where we produce the foods. And so we'll have the ability to keep those habitats at a tolerable level for the plants. But you do raise an interesting issue, is again, back to how, you know, how cold, how warm are these temperatures are these plants able to tolerate? We've had lots of issues with our exolabs in terms of temperature problems. That the environment on the space station is actually very warm. If you think of all the electronics, all of those give off heat. And that's going to be a situation in any enclosed habitat. In my small office here, I've got all these lights for the plants, the experiments that I'm doing right now. And I would say my office is a good 5 to sometimes 10 degrees warmer than the rest of the house is. And it's actually at times been too warm for my seedlings. They've started to germinate and then died, or bacteria attacked them that was in the air because it's so warm.
And Michael, if I can add, I think kind of Richard may have addressed this earlier, is on the surface of Mars, you have significant radiation. And so all these beautiful artistic representations of greenhouses on the surface is going to be highly unlikely, at least at first, until you figure out how to shield even the plants from the radiation. As humans, we need shielding, but the plants are going to need shielding too, because they too will suffer DNA damage. And so you're talking about controlling temperature, pressure, humidity, oxygen and carbon dioxide levels, and then dealing with that radiation factor. So some have proposed using underground lava tubes for habitat as well as greenhouses. And that definitely will mean artificial lighting. And so that'll be another determining factor for what kind of plants you can grow, is the right lighting. And how
that was the question earlier that somebody asked was what are our energy sources? What are our potential energy sources on Mars? Can we use anything besides solar safely?
Right, because there's huge power and electricity demands to run all of these environmental control systems.
So there's some engineering challenge, students. So you're like, I don't really care about the plants. I know we got to eat, but you know, I'm not so fond of vegetables. I could live without them. You know, all those things. But I bet some of you are into engineering and the mechanics and the electronics, and I know some of my students are really getting into coding. Those are all solutions that have to be sorted out. And I know for me personally, that's one of the most compelling things about the space program. If you want to be in the space program, there isn't a single career that you can't find a home there. Whether you're an artist, an engineer, a chef, I mean, it's an accountant.
Space chef.
So, you know, that's if you want to be involved in space exploration, you don't have to go to space to do it. You can be part of those tens of thousands of people who make it possible for those 3 astronauts who are on the space station right now to be there. And if those who don't know, the previous 3 safely came home this morning. So our U.S. astronaut, Christina Mera, she's back on terra firma. And we actually have a family connection through our school. So maybe if you're paying attention, Jessica, wink, wink, nudge, nudge, know what I mean? And I know Diana has a little connection as well. So what we can do.
There you go. Hey, Michael, can I make a comment about observations?
Please.
And so I'm kind of turning back into a young kid again, which is exciting for me by doing some science experiments with everyone. And so what I've tried to do is actually activate all my senses, which I kind of have a tendency to turn off when I'm doing my day-to-day. So I'm not just doing visual observations, but in order to kind of keep my plants from being contaminated for mold and what have you, I've been covering them with a just like a little glass aquarium to cover all my plants. And when I take it off in the morning to kind of take a look at them, I get a waft, a smell that's different. It smells like apples right now, but separately, like glycine max, it looked kind of stinky when it first got started. And these others, I didn't smell anything at all, but these are having different smells. So I'm wondering, as they go through the process of taking in the carbon and turning things back into oxygen, they're giving off other stuff. So when we think about these plants and their benefits, I'm starting to ask myself, well, what kind of research can I investigate to think about what else these things can do? And I'm looking at the way they develop and they're growing their roots, and some of them really thick right away, some are just waiting around. I think they're going to really just explode. Some of them just pop up really quickly. So we think it all happens the same way. They're all different. They're all doing different things. That's how they've evolved, I guess. And we're trying to find a kind of something similar. I've got a little terrarium, I guess if you want to say that, with a couple of different ones in there, and they're all doing different things. They all were started at the same time. And this is just some aggregate, like if you're going to go out to the baseball field and you're going to run around the bases, this is the stuff that that they have on the field or the track if you're going to go running. And then I put some of that agar that you might have used in your classrooms already. And it's most of it has absorbed into the clay. So I'm thinking this thing's going to stay hydrated. In microgravity, though, it'll probably be floating around. So I don't think I can do it that way. But it's very interesting to see. So think about smell, taste, touch, you know, also just that observation. Listen, I don't think they're making any noises, but my ears aren't that good anymore. Maybe they're actually even some sounds. I don't know.
Well,
but don't put anything past your senses.
Richard's told us that the plants actually respond to sound. Can you?
Yeah, that was pretty wild. That might be an interesting test just on the side for fun, right?
Yeah, yeah.
So what are the couple of things that he described for us?
Well, the sound of running water they would go toward.
Right.
And they also exhibit a stress reaction for the sound of predatory insects.
Exactly. So I wonder if they make themselves taste bad, right? Wouldn't it be cool if a bear was chasing you and you just, I'm going to make myself smell bad? It's like.
So my students know how important this little elixir of life is to me. So I'm looking at one of the growth media that I'm trying. This one's 100% coffee grounds with a little bit of that agar on the top of it. And this is a mung bean.
Vignangularis.
Mm-hmm.
And it's doing really well. It likes that environment. This is another.
Steve was doing coffee also, right?
Yep.
Is anyone else doing coffee as a grounds? I know you're doing tea, Dana.
I will be.
Try that. You got something, Renee? What are you using?
I said I will be. I just started my germination process.
Yeah,
so.
I told my son and my wife that don't throw the coffee grounds away. I got to experiment.
Yeah, I did the same.
I'm using Big Bang, by the way, Pete's Coffee. I really like the name. Big Bang.
Say that people can keep track of all the different names and varieties that they're using, and because a great comparison can come out of that.
Oh, there you go. Right? Is it a dark
that's a
roast?
great idea.
Light roast.
My students, Death Wish.
I don't know what John will have to
I did all
ask.
kinds of, yeah, Michael's. They can say I can never get too much death wish. I tell them I only drink 1 cup a day. It just never gets empty.
There you go.
So I got a great question for this crew. What's so special about the ExoLab?
What's so special about the ExoLab? Here's the amazing thing.
Who asked that question? I got to find out what that was. Avery.
So typically there are a couple different ways that you can run an experiment beyond Earth. You need to have a connection with the Department of Defense because you've got some military application. Or you're working with NASA because they're doing some deep research and you're a doctorate of such and such, and you're going to figure out a new medicine, or you're going to grow brain organoids or something. Or there's a group out there which we are eternally grateful for, called the Center for Advancement of Science and Space.
Please mute your mic.
CASIS, which is also known as the U.S. National Laboratory. And they enable us to send an experiment up there. And the big differentiator between ExoLab and everything else that goes up today to do research is we fly a single experiment, and it's not inexpensive. It's pretty expensive to send something up there. But we open that experiment up to students around the world. So you're in Brooklyn or you're in New York, and we've got students in Kenya, we got students in Hamburg, Germany, or in Osaka, Japan, and they're running these experiments, and they're connecting with that space station, that single experiment. And so we're able to take something that was generally expensive, and we make it very affordable. And in fact, through this program, it's even free for the first couple phases. So we have a chance to get students that may normally not even have a chance to do something, to experiment and imagine what might be possible. And to me, that's everything. Being able to have students that normally don't have a chance to do this, be able to have that opportunity, because they're just as smart as anyone else. They just need to be given that opportunity to experiment. And so I think that's probably one of the most exciting things, not really so much about technology, so much as it's an enabler. It's like you can ask, what good is your phone for? Making phone calls, but it does many other things. But really what's important is it connects you, right? Connects you to knowledge, and connects you to people that you know or people you'd like to know. And so that's kind of what ExoLab does. In a way, it's an enabler. It connects. And
I think it's so cool how Erica takes an ExoLab out to the bush in South Africa with a satellite phone and a generator, so that people who have they're totally off the grid, they've still been able to participate in this research with us.
There you go. And I'm going to have to today. We can keep it running, but Tony and I have a hard stop at noon today. A pretty important conference call.
Yeah, I think for all of our listeners,
are so exciting, and
they've had a long day as well. So I think we can try to do this another day. There's some other questions, and there are questions here that are really. I just want to share this one, and maybe that's a good one to close out on.
Okay.
This is from Rory. And essentially, it's a really long question, so I'm paraphrasing. He's wondering, okay, he gets that there's microgravity stress. He gets that there's temperature stresses, all the different things. Could we put plants through a staging? And then, if I'm understanding his question correctly, using the seeds from those plants, so basically do some genetics work to create plants that would have an even higher potential of surviving those stresses.
Oh yeah, that'd be great. And so maybe if you want to do this, you look at a model organism, like Dr. Barker earlier was talking about Arabidopsis as a model plant. The fruit fly is a model organism for insects because its life cycle is so short, right? And so if you want to go multiple generations and just study epigenetics and protein sequences, and way above what I know, but you want to look at it for a fast life cycle, I think. And so you can start discovering 5th generation mung bean or glycine max. What's it going to do? How will it, and in on the moon, is it going to be different than on the space station or here on Earth? And I guess if you think about it, going back to your teacher's favorite drink, coffee has different tastes in different parts of the world. Why? Right? And yet they're all coffee beans. A lot of it's from Arabica, right? But they've diversified through generations. And so can we do the same and think about what qualities you might want to see in your food and think about what might be in the environment that can help bring those qualities out? And who knows, maybe you end up growing wine in the future or something like that, right? Well, guys, it's always fun with these sessions. And the students that had questions that didn't have them answered today, if you want, we'll work together as a team or do another session just with you guys and Michael. We'll get those answered for you. I know how excited you are. And for anyone listening on YouTube or on Facebook or our teachers here in Zoom, if you want to get your classroom involved and engaged in a conversation with others, teachers from around the world, just send us a note, hello@magnitude.io. Limited slots. I can't guarantee that we can get you on, but we would definitely love to hear from you. And if we've got the time and the opportunity, we can also just hold a separate session just for you. So keep that in mind as well. Our objective here with Magnitude and what we're doing with Exolab 8 is our planet is kind of getting crushed right now under this interesting pandemic scenario. We want to reach out and say we've one world, we're all in it together. Let's build a community. Let's have some fun and think about things we can control and understand rather than things we can't control so much. So, and have a wonderful weekend. We'll catch up with you guys next week. Hopefully our balloon comes back from its descent. It was supposed to go across the United States and it looks like it wants to land somewhere because of the rain or the wind. We're going to keep an eye on that. So watch that and hopefully it's going to pop back up in a little bit. So until next time, you guys have a wonderful weekend.
You guys have a great weekend. You're free to sign off. And I will see you on Tuesday.
Tell them thank you from all of us, Mike.
You've had lots of big thank yous and impressed adults here. So
thank you, guys.
Thanks all.
Thanks,
Space station over Canada right now, by the way.
What?
Oh, over Canada.
All right.
Perfect. It's touched everybody.
Okay, I'm gonna run outside, even though it's snowing. What the hell?
That's right. No, just